Oops. Hi, Kunlun. Good morning.
Good morning. How are you?
Yeah, how are you?
Very good. I don't see the people. Let me see.
So I think we will start at 9:05. It will be okay?
That's fine. Yes.
Yeah, good.
So, Hicho, can people see me there?
Sorry?
Can people see my face there or
Yeah,
not?
yes, we can see your face.
Okay.
Yeah. You are in your home now?
Yes.
I see. So students are still coming, so we'll wait just 2 minutes and start.
Sure. No rush.
So you can see the audiences, right? So we installed
Yes,
the
I
two
see the
cameras.
audience. I cannot pin it for some reason. I don't know why.
Uh-huh.
So it looks very small. I cannot see too well.
Okay, good morning, everyone. So let's just start today's program. We'll have 3 lectures today, and first lecture will be by Professor Kunlun Buffer. He will be talking about his third lecture about string landscape and swampland. And please.
Thank you. So this is going to be my final lecture on the topic, and it's going to involve basically applications of the swampland program to our universe. I cannot cover all the swampland criteria. I have only covered a few of them, and more descriptions of all the other criteria are in my lecture notes. So if you are interested, you are welcome to take a look at it in more detail. The applications I have in mind to show you today will follow from the criteria I have already described. So it's consistent with the plan of the first 2 lectures to conclude with the lecture I'm giving today. So the basic idea is to apply to our universe, but in order to do that, I also want to give one more criteria, which is the de Sitter conjecture, or more precisely conjectures. There are 2 different de Sitter conjectures. I'll describe them both, and I briefly describe their applications also to our universe. But bulk of my talk today will involve the last topic, which is the dark dimension. And I try to explain why, from the criteria I have already mentioned to you, it is naturally suggested that we have one extra mesoscopic dimension, which is relatively large. And it has very interesting phenomenological implication. And this is a good example to show that even though the criteria we're talking about in the context of swampland is to rule out theories, it can nevertheless be used to predict theories. So in other words, it's not a negative statement in the sense that it's sufficiently restrictive to actually tell you what can happen. And that's also another reason I want to discuss the application here. And the good thing is that that applies to our universe, and it's actually being experimentally tested as we speak. So people are trying to measure it, the consequences I will actually mention. Before I start, though, are there any questions from last 2 lectures? No questions. Okay, so if there are no questions, then I will start my lecture for today. So there are various applications that one can envision to our universe. I will just describe a few of them. I'm not going to be comprehensive. I'm just going to give you examples. It is difficult to give you all the applications, but there are some simple ones. I will start with actually the 0th order application. The 0th order application is that the dimension of the space-time is 4. Now, you might say, what kind of an application is this? Well, actually, you could imagine the dimension of space-time to be arbitrarily large. And if you were to take a random number from 1 to infinity, the average will probably be infinity if you have any reasonable measure. And so therefore, it's surprising that the dimension of space-time is so small. Of course, in the context of string theory, we know that the highest dimension you can have is 10 or 11, depending on the limits you take. But you cannot get too high a dimension because of supersymmetry doesn't exist in those dimensions. So in some sense, already string theory is predicting something having to do with the dimensions being less than or equal to 11, and this is a prediction of string landscape, and in some sense the swampland, because it turns out that the non-supersymmetric solutions in string theory are relatively unstable. So you have at some point to be connected to some supersymmetric case. But nevertheless, this item number 0 is not really a prediction of swampland, but more a prediction of string theory. So let's not describe this too much. Let's go to criteria application 1. And this is again some kind of a meta application. The rank of the gauge group of the standard model is small. It's certainly less than infinity. In fact, it's even less than 10. SU3 cross SU2 cross U1 has rank 2 plus 1 plus 1. So the rank is very small. So why is that? Well, it's not a priori obvious that this has anything to do with swampland criteria, but actually it most likely does, even though we don't apply it directly to the theories with no supersymmetry. We already know that for theories with higher supersymmetry, In fact, the highest supersymmetry with matter in 4 dimensions is n equals to 4 supersymmetric theories in 4 dimensions. The rank of the gauge group is less than or equal to 26 minus t. This follows from a swampland ideas. And I want to give you a sketch of this, how this kind of thing emerges. Part of this was related to the work we did actually with Hichio. And so this was already discussed in some other papers with him, but also we developed it further. And it gives you some relations of this type more generally for any dimensions. And the idea is rather simple. So let me explain the basic point. The basic point is that if you consider theories with 16 supercharges as a theory with n equals to 4 would demand, for example, or the 16 supercharged theories demand, then we can use the completeness hypothesis to conclude, because the supergravity multiplet has an antisymmetric BMU field, that there must be a string. This is the completeness of spectrum argument applied to BMU field. Strings exist. The strings which are charged under this BMU. More than that, actually, anomaly inflow argument, by saying what flows into from the ball to the string, you find an expression for left and right central charges of the theory in the infrared moving on the string. And you find the central charge is, depending on the two cases that you have, in one case is less than or equal to 26 minus t. And this will give you that the rank of the group is less than or equal to 26 minus t. Why is this? How does this follow? Well, it turns out that by unitarity on the string, it tells you that the rank is less than the central charge. This is a theorem for the Cosmology algebras. So therefore, since you know the central charge, you learn that rank is bounded. So you give an example. This is an example of a situation where we use ideas from completeness, unitarity of the theories living on the string, to deduce facts about the rank of the theory in the ball to be bounded. Even though n equals to 4 Yang-Mills for any gauge group is a perfectly fine theory, and in 4 dimension, in fact, it's conformal, you find that only a finite number of them are allowed to appear in the quantum gravity landscape. This argument does not use string theory. It's general. And therefore, we are learning some facts about quantum gravity from simple ideas like this, completeness of hypothesis and so on. So this is another application. Therefore, if we live with a theory with 16 supercharges, we have a bound of rank 22 if you put d equals to 4. So in d equals to 4, if it were n equals to 4, we get the rank is less than or equal to 22. Of course, we don't live in a 4-dimensional theory with 4 supersymmetries. In fact, we don't have any supersymmetries. So we cannot use that to argue a bound, but it's consistent with this general idea to expect that rank is bounded. It's not too big in some sense. Well, it could be in some examples in string theory very, very big, but my point here is that it's not like arbitrarily large number. Okay, so that's the other application. Other application, that there should be no global symmetries. This is true in standard model, except what we discussed already about the B minus L, which should be B minus L symmetry is a symmetry. And we know that it's either, according to what I have told you, it should be gauged or broken. So we already are making a prediction about this properties of standard model that you have to make your choice. One or the other has to happen. Either B minus L symmetry is broken by weak effects, or it's indeed gauged weakly, because otherwise we would also know that. So that's another example of an application. There's another application having to do with the weak gravity conjecture and the Festina lente that we discussed last time. And it gave a bound to the mass of the, let's say, the fundamental field, charged object, for the U1, let me call it electron. It may not have been electron because it could have been a multiple charge of the electron, but something like mass of the electron should be less than the Q. So there was this formula, square root of Q times lambda to the 1/4. So this basically gives you mass of the electron is less than or equal to 0.1 m Planck, because I'm using the fine structure constant, which is about 0.1, square root of it, that is. And this should be bigger than or equal to some number here. And this number is actually roughly of the order of the mass of the neutrino. So you learn that the mass of the electron is bigger than the mass scale of neutrino, but smaller than the Planck scale by 0.1 Planck scale. Of course, this is true. But in fact, the interesting thing is that if we had measured the mass of the electron, which we had, but before measuring this for cosmological constant, we could have predicted an upper bound to what the cosmological constant can be. In fact, you find that the cosmological constant, just from this side, I don't remember the exact number, but maybe it was something like 10 to the minus 88 in Planck units. So therefore, even though lambda ends up being 10 to the minus 120, the fact that it had to be small already follows from these principles. Namely, it's at least 10 to the minus 80. It should be at most 10 to the minus 88 or something like that. Another application, completeness hypothesis, tells you the magnetic monopole exists. Because completeness doesn't only apply to electric, it also applies to magnetic. Now, in the grand unified theories, we have examples where magnetic monopole appear, but here I'm saying that we don't need to know about whether there's a grand unification or not. There always has to be a magnetic monopole. More than that, the weak gravity conjecture makes a prediction that the mass of the monopole is less than or equal to 1 over square root of alpha times m Planck, because the magnetic charge is the inverse of square root of alpha. And this gives you something of the order of 10 m Planck. So that means you learn an upper bound from the magnetic monopole, which is 10 times the Planck mass. These are already quite remarkable because we're just using some basic ideas to make predictions in principle observable in our universe.
There is a question from Zoom.
Yes?
The question is there a lower bound for scalar masses somehow?
Not really. People have tried to extend the weak gravity conjecture to scalar fields. If they were charged, they could have been, but not for non-charged ones.
Okay, thank you.
Okay, so that's another
excuse me?
application.
Somehow
Yes.
for the charged particles in the spontaneously broken gauge symmetries, would the masses of those particles could be constrained somehow?
No, because these arguments rely on having a macroscopic stable black hole, but not stable, but macroscopic long-lived black hole.
So it has to be
Of
unbroken.
charge.
Yeah, okay.
But if the charge is broken, that's very unstable.
Okay, thank you.
Yeah. In a sense, let me just go back. If you look at the festina lente, this relation over here, this part of it, if you applied it to the electroweak SU2, then you might have deduced that the mass of what would be the neutrino would be of the order of the neutrino mass, which is the lower bound. So in other words, the fact that the neutrino mass has something to do with the lambda to the 1/4 would have been followed. But we know SU2 is broken, so we cannot use this argument. However, this can be used in some other cases to make predictions. For example, this is something I'm not going to talk about, but if you talk about inflation, people often draw a model like this, where you have a potential which is a flat region, and in terms of the inflaton field, and in this region, you have a lambda. Now, there's a strong restriction here because the mass of the fields here should be bigger than lambda to the 1/4. So this gives you the restriction that the lambda should be less than or equal to whatever the charged objects are to the power of 4. So this is a restriction of what masses lambdas can appear. So there's high scale inflation field will be in trouble, because if you have a flat region like this, which we usually want, because it behaves like de Sitter, and it gives you a puzzle with charged particles like electrons. So already gives you a strong restriction on the inflation. Okay, so but I want to talk about something else. I want to talk about the de Sitter conjectures. We live in a universe for which lambda is positive. We seem to have dark energy. We do not know if it's the dark energy is stable or not, and we do not know if it's exactly constant or not. So usually we try to get this using a potential, maybe a metastable potential somewhere, or maybe even sufficiently slowly rolling potential like this. And the value of lambda will be either the minimum, which might be metastable, or some value on this rolling potential.
So there is a question from Zoom.
Yes?
Sorry. The question is a question on the general principle. Since we are constraining theories with which could couple to gravity, what says the swampland theories cannot appear as boundary non-gravitational dual?
Boundaries as boundaries of non-gravitational dual,
Yes.
I'm not sure exactly what you mean, but I'm only talking about the gravitational theories. So for example, SUN Yang-Mills for arbitrary n with n equals to 4 does appear as a boundary of a quantum gravity theory. I am not talking about that. There's no problem with that. What I'm saying is that there cannot be an SUN Yang-Mills in the bulk coupled to gravity with n equals to 4 if n is too big.
Okay, thank you.
Yeah. Okay, so these are some of the examples the way we think about the potential. Now I want to argue the following. In string examples, when you go to weak coupling, which is the dilettante going to infinity, we always find that the potential falls off exponentially. We find something like V goes like e to the minus some alpha phi in all the examples in string theory. In fact, this leads us, and the values that we get for this alpha seem to be order 1 in Planck unit. This leads us to the statement that V prime over V, the slope, which gives you the alpha, asymptotically, this slope is of order 1. And in general, it's bigger than or equal to order 1 number, one might conjecture. You cannot make it small. You cannot make it too small. We always get bigger than some order 1 number. So this was conjectured that maybe V prime over V is always bigger than or equal to order 1 number. But there are situations in string theory where you seem to get a maximum to potential, in which case V prime vanishes. But usually when this happens, in fact, in all the cases that this happens that we know of, the second derivative of V is very negative. In other words, it's bigger than order 1, the second derivative in absolute value. In other words, it's sufficiently unstable that it wants to drop down from the potential. So in other words, this is basically telling you, you cannot have a quasi-stable situation if you are in this situation. This conjecture is motivated from the fact that for weak coupling, we know something like this is true, but we really don't know what's going on here in the interior when it's not weakly coupled. So this is just really a guess for the interior. But for the boundaries, we already have a lot of evidence that this is true. That by boundaries, I mean when you go to the extreme values of the field, like weak coupling. In fact, we can give a simple argument for it. Let me explain. I want to show that the distance conjecture together with Higuchi bound gives you this relation. So let me explain that. This is conjecture, remember, I told you that the masses of the fields that the tau that you get is going to be, the mass is going to be less than or equal to e to the minus, sorry, the mass goes, let me say it this way. The mass scales like e to the minus some exponent times phi, where lambda is bigger than or equal to 1 over square root of d minus 2, as we discussed last time. Now, if you have such a massive state at far, so if you have large phi value, you have some massive theories, you could ask, what's the relation between V and the mass? The potential and the mass. Which power does it scale like? There is one thing about the tower. So this is not just for some mass coming down, but there's a tower of them. And this tower always has a spin 2 object in it. Why? Because it's either KK tower or string tower. So that means there's this massive tower. It includes at least a spin 2 field. For spin 2 fields, there is a bound by unitarity. If you had the de Sitter situation where you have a constant potential, that V, or let me call it lambda, in that case, that the mass is always bigger than square root of V, or lambda to the 1/2, or in this case, V to the 1/2. In other words, m squared should be bigger than V. So V is less than m squared. But m is less than e to the minus phi over root d minus 2, we just said, for large phi. So m squared is less than e to the minus 2. In other words, you learn from this relation that V scales less than this. And this gives you a bound on the exponent. Namely, it tells you that V prime over V is bigger than or equal to 2 over root d minus 2. So the combination of the distance conjecture and this is called the Higuchi bound, which follows from unitarity for spin 2 in a de Sitter space. This is the mass of spin 2. So this relation that the mass of spin 2 is always bigger than lambda to the 1/2 gives you a restriction about the slope of V. And this is true in all known string theories, this bound. That means that for weak coupling, you always find it falls off like this, or faster. This speed of falling off actually implies that asymptotically, you cannot get an acceleration. So our accelerating universe cannot be as arbitrarily large value of phi, because this does not allow it to give you an acceleration. So if we have a situation where we are having a quintessence-like field, it should be a little bit farther from infinity. It should be somewhere a little bit more towards the interior, according to this statement. Okay, so this is one de Sitter conjecture, but you see the de Sitter conjecture, I was just describing it. What happens at the asymptotic values when you go to faraway distances? And here we just argued that V prime over V should be bigger than or equal in slope to 2 over root d minus 2. But what about the interior? The interior of it, which is far from large distance, we don't have as much analytic control. There's no distance conjecture. We don't have any of these kind of statements, and we don't have any analytic tools to study them. When you break supersymmetry and you're far away from the weak coupling limit, we don't have any tools. So we really don't have a good argument here, what it should be. So the question, the de Sitter conjecture I just told you was trying to extrapolate and say some equation like this, V prime of V is bigger than order 1, still holds. This order 1 may not be this number anymore because you're not at asymptotic infinity. But the question is that maybe there's some order 1 number for which this is still true, or that it's sufficiently unstable, the way we just described. But it's hard to motivate this from why it should be the case from the interior. There is another version of the de Sitter conjecture which actually does predict this value asymptotically, and it's kind of motivated by some quantum gravity. So let me explain that. This is called the Transplanckian censorship conjecture. Transplanckian censorship conjecture. And the idea is that suppose you consider an expanding universe of the form minus dt squared plus a of t squared dx squared. Suppose you start looking at the patch which is smaller than Planck length. And as the universe is expanding, this grows. This region that was small grows and grows and grows. If this region that grows becomes bigger than the Hubble scale, which is h to the -1, if it gets bigger than that, then it freezes, because that's the way the modes classicalize. But what that means is that if you start with the sub-Planckian modes and then classicalize it, that means that somehow the modes which were inaccessible, which didn't mean anything because we don't think distances less than Planck scale should make sense, somehow become visible classically, and that sounds strange. In other words, you get to the conclusion that the final A of expansion, which amplifies the L Planck, cannot be bigger than a Hubble length. So the final to initial expands the L Planck, but it cannot be too big. Now, suppose you, for example, have just constant inflation, constant like minimum, and then the expansion of the universe will have an expansion of the form e to the ht. And the relation I just told you tells you that you get into trouble if e to the ht final is bigger or equal to h inverse. And if you take a log of this, that means that you get into trouble if t is bigger than or equal. There'll be trouble if t is bigger than or equal to 1 over h log 1 over h. In Planck units. So that means that what could happen is that they cannot have such an continuously inflating universe. That means the universe should stop making sense at that scale. In other words, there's a decay time which should be less than or equal to 1 over h log 1 over h. So we are predicting using this principle that there should be a maximum decay time, which is of order of 1 over h log 1 over h. For our universe, this is about 2 trillion years. So this would give you an upper bound for our universe of order of 2 trillion years. But this even though it's kind of heuristically motivated from Planck physics, we can actually do better. You can use the Transplanckian censorship conjecture to see what happens for potentials. You can ask whether or not you can have a situation where A of t, which is the expansion, when you're on a potential, it leads to similar problems. And when you look at it asymptotically, you find that v prime over v should be bigger than or equal to 2 over root d minus 2. So this fact can be predicted from TCC, which we argued differently from distance conjecture and from Hikuchi bound. So already we get it 2 different ways at the same conclusion, but the TCC therefore gets to be even predicting the value at infinity. So the TCC tells you that in principle, there could be a metastable minimum as long as the lifetime of it is not too big. As long as the lifetime is less than or equal to 1 over h log 1 over h. And if you put the cosmological constant for our universe today, you get the prediction of about 2 trillion years as the upper bound. Now, there are 2 important questions in cosmology that are puzzling that I want to, there are many questions, but there are 2 important ones that I want to discuss today. 2 important questions of cosmology.
Excuse me.
Yes?
What happens if you apply to inflation, the previous argument?
Inflation will have, the inflation is going to be highly restricted if you consider TCC. So high inflation would not work, for example.
Ah, okay. Thank you.
High scale inflation would not work. Inflation has problems with also other swampland criteria. So inflation has many potential tensions with a lot of these criteria we're getting. But anyhow, I'm not going to talk about inflation today. Not too much anyhow. So there are 2 important questions that I want to remind you or tell you about in cosmology. One question, one statement is called why now. Why now question is that we are living in an epoch in the universe that we are considering, we are getting an accelerated expansion. So that gives you some value of lambda. That, I mean, the expansion comes from the cosmological constant. But this value is actually in a situation that why is it that at this point that the lifetime that we are having is compatible with the scale that this defines? Namely, there's a Hubble scale, Hubble time, which goes like lambda to the -1/2. This gives you a time scale. The question is why the time that we are living now is of the same order as this Hubble scale. In other words, if you wait long enough, if you had this lambda, the universe, this time now grows, but this doesn't change. So it's surprising that we live exactly in an epoch where the time now is the Hubble time. Now, this is one of the puzzles in cosmology, and I claim this is already solved by the TCC or the de Sitter conjecture. In the TCC, for instance, we are saying that this is the case because the lifetime of the universe is bounded by 1/h up to log 1/h factors. So in other words, if you take a lifetime, or if you take a sample times in a universe whose lifetime is 1/h log 1/h, the natural scale will be of the order of 1/h. So that tells you that the fact that we have been getting this puzzle of why now is related to the fact that the universe is going to come to an end relatively soon in our universe. The measurement of dark energy is going to basically describe or give a rise to a prediction also of the demise of the universe, a lifetime for it. So that will explain the why now problem. So the de Sitter conjecture is an answer to the why now problem. There's a second question in cosmology, which is called the coincidence problem. Coincidence problem tells you is the following. So if you consider the density of various fields as a function of the time in the universe, I'm going to be heuristically drawing this, not accurately. At the beginning, the radiation has the highest energy density, and the matter had less. At some point, the matter becomes dominant, and the radiation becomes subdominant. So they're both going down, but one of them is subdominant now. But it turns out that precisely at that point, or very, very shortly thereafter, the dark energy takes over. So in other words, the coincidence is that why is it that where radiation and matter cross is also very close to where the dark energy takes over. So if I want to draw them a bit better, you have these three lines which come very close together instead of like this. So you have first radiation and then matter, and then very shortly thereafter, the dark energy takes over. Why are they so close? Why is it almost coincide? In other words, why the matter radiation equality temperature is the same temperature at which the dark energy takes over. This is called the coincidence problem in cosmology. I will give you a solution. I will explain this potential solution to the coincidence problem after I talk about the next topic, which is going to occupy us for the rest of this lecture. And this is called the dark dimension scenario.
What happened to the decay of the universe? I mean, you said that there is a lifetime for distant space. Then what's the dynamical process where universe decayed? Or
Lifetime for our universe?
yeah.
Yeah, I mentioned 2 trillion years is the upper bound if you take TCC.
Yeah, then what happens after that?
Oh, we don't know. So all this predicts is that it should decay to something else. So it doesn't tell you what happens next. So for example, if you're like this, you have a decay like this, and we do not know what happens. It starts rolling down, for example. We do not know what's here. But one thing it says, when it says the lifetime is of order of 1 over h log 1 over h, that means it's not justifiable to call this really de Sitter, because the lifetime is given by the Hubble scale also, up to a log correction. So this is sufficiently unstable that whether we call this de Sitter or not is up to us. But in particular, it means that you cannot have a big barrier here. The barrier should be very shallow, so it could be like this, very, very easy to escape out. So in principle, you can have a situation where you have these barriers which give you an effective rolling with a much smaller slope. And this one we studied in a different paper. But anyway, I'm not going to talk about that aspect.
Yeah, so I have another small question.
Yes?
Yeah, so I think in the slide before, a couple of slides before, you showed the now problem. Yeah, this one. So is it possible that this lambda is also very weakly dependent on the time?
It could have been. But in other words, you want to say that this somehow goes on like this, but that's not, that would have been perhaps too much of a slope.
I see.
In other words, the variation of V prime is not that long. In other words, so let me say one thing. We do know that V prime over V of observed universe is less than or equal to something like 0.2 or 0.3 in our universe.
I see.
So it cannot be varying too fast.
Yes, but it could be very weakly dependent on time, I suppose.
Yeah, but I don't think it will resolve this problem.
I see. Okay. Thank you.
So let me go to the dark dimension scenario I wanted to mention. The dark dimension scenario is the following observation. Last time I told you that in the context of de Sitter or anti-de Sitter, you expect a tower of states of the form of m is equal to lambda to some power. A tower of light states. Now, that's only if lambda is small. In other words, if you're in the extreme limit, the distance conjecture or generalized distance conjecture predicts that there's a tower of light states. But lambda is a very small number in our universe. It's 10 to the minus 122 in the fundamental units. So indeed, it's extremely small. And so therefore, the scenario predicts that you are in a very large distance regime, and you might expect, therefore, this to be valid for some alpha in our universe. That means there's a tower of light states which goes like lambda to the alpha for some alpha. So tower of light states. Light particles, which scale go like this for some alpha. And the question, of course, is what is the alpha? But before I answer that, I claim that this already gives you a pseudo solution to the cosmological constant problem. So let me try to explain. We say that m should scale like lambda to the alpha as lambda goes to 0. But that means also that lambda also scales like m to the 1 over alpha, where m is very small. In some sense, when m is going towards 0. But this is strange. This relation tells you that if you're getting this light tower of states, the cosmological constant is determined by the light tower, by the mass of the light tower, not the heavy fields. The cosmological constant problem is exactly this, that why don't you get a contribution from the heavy objects, or like m Planck, to the power of d? Why don't you get a cutoff dependence like this? And here we are saying that the distance conjecture say that's not true. In other words, the more natural quantum field theory prediction would be lambda might get a contribution from some light particles with some power, but you also have some constant in addition coming from other degrees of freedom. The distance conjecture says this is not possible, and indeed lambda naught has to be 0. That the miraculous cancellation of higher massive states is necessary for the distance conjecture, or more precisely, the generalized distance conjecture to be true. Let me explain this because this is actually a crucial point, And I will try to give you an example from string theory for which this does happen. Consider bosonic strings. And consider, well, bosonic string has tachyons and all that. You might say, why are we doing this? But take the extreme small limit. In fact, G string goes to 0 limit. In this limit, you only have the 3 diagrams, and there's no problem with the tachyon a priori. You just have the 3 diagrams. And you can ask, what is the cosmological constant for bosonic string theory? There is no supersymmetry, so there is no cancellations between bosons and fermions. But we can still ask, what is the cosmological constant for bosonic string as G string goes to 0? From worksheet diagrams, we already know the answer. The answer should be 0. The cosmological constant for bosonic string theory at G equals to 0 is 0. How does this work? This comes because this is going to be some value of the free energy at genus 0 divided by the volume of the SL2C symmetry, because there's a sphere diagram with no insertion has SL2C symmetry. You have to divide it by the symmetry group, and this is infinite. So you have some constant over infinity, which is 0. There is no cosmological constant. So the vanishing of the cosmological constant for bosonic string is not because of supersymmetry, because of conformal invariance of strings. This is surprising from the viewpoint of effective field theory, because bosonic string has huge number of fields now, which have no fermions and bosons. It's just bosons. Of course, you might ask, okay, so but bosonic string is not complete, because then we can go to one loop and get corrections. What about that? In fact, in that case, you know it's tachyons, and so the whole thing is going to be readjusting itself. So this is not necessarily good. But let me remind you that as G string goes to 0, you get a tower of light states. And the tower of light states are the string modes. And the mass of the string state goes like G string to some power. So indeed, as G string goes to 0, you do get a relation like lambda goes to m to some power, because indeed they both go to 0. So this is actually true in that case. So the fact that the higher modes don't contribute is already true in that case, and it is a consequence of conformal invariance. But let me actually give you a little bit more satisfactory example, because I was just saying that it's a tree level. You might say, what about the one loop effect? Or there's tachyon there. However, we do know there are bosonic string theory with no tachyon. And so consider all 16 cross all 16 strings in 10 dimension. This is a string theory which is not supersymmetry. So there's a non-supersymmetric string in 10 dimension, which is chiral, and everything is nice about it. It just doesn't have supersymmetry. The genus 0 answer at genus 0, the lambda is 0, as we just discussed. But now you can go to one loop amplitudes and compute the cosmological constant. What is the answer? Well, from what I just told you, you would expect that lambda should go like the mass of string states to some power. And indeed, that is the case. You do the one loop computation, you find it goes like m string to the 10th power with some numerical factor of order 1.
Excuse me, I have
Yes.
a quick question
Yes.
from the previous slide.
Yes.
How well understood it is to compute the sphere partition function? Because I don't remember the details, but I remember seeing a paper by Maldacena and other people for the 2-point function where perhaps there could be a similar argument that it should be 0, but there are some subtleties.
No, not for the 2-point function. 2-point function is not 0 a priori.
But couldn't you say there that there is also
No, you have to pin a point, 2 points.
but to remove all the conformal invariance, you need 3 points, no?
Let me think. Yeah, 3 points. My argument says that for 3 points, for sure, there is no argument.
Yeah.
Because you have SL2C completely frozen. For 2 points, you have still the rescaling invariance. That's true. Z goes to lambda Z, for example. There's a non-compact one.
Yeah, nevertheless, I thought in that paper they show that it's still finite. They don't do it for the sphere, but I was just wondering if there could be a similar subtlety.
No, for the sphere, you don't get correction. You can get correction from one loop, for example. So at any rate, the main point is that this fact is well known in bosonic string theory. And by the way, I should say this argument that I was just telling you is due to Witten, that the volume of SL2C is one way to understand why lambda is zero. Of course, we know it is zero. The bosonic string theory does not have a constant in Einstein's equation at 3 level. But this is a way to explain it, the SL2C symmetry. It's conformal invariant. Now, if you go to 10 dimensions and you do the one loop computation, you find lambda goes to like m string to the 10. But actually, this is also strange because as G string is small, as G string is much, much less than 1, M string also goes to 0, is much, much less than 1 because it scales like some power of G string. So this is exactly the relation that lambda goes like a power of the light states. M string is very light in this limit. Indeed, what happens there is that if you do the computation in string theory, if you do the computation, you would think that the actual computation is you end up the computation on the fundamental domain. So string theory tells you you have to cut it off by some region and do the integration in this region. Whereas the field theory will say, no, you have to compute this in this whole strip. The field theory does not know about SL2Z symmetry. But SL2Z symmetry tells you that you only include the effects up to this fundamental domain, this red circle. If you cut it off there, these modes don't contribute, and these are precisely where the Planckian modes contribute. So when the field theory tells you that there's a cutoff, that lambda should go like m Planck to the power of 10, and then you cut it off by m Planck, this is because m Planck modes are here. But string theory tells you no, before you get to that, the SL2Z cuts it off. So again, a symmetry of string theory comes to the rescue. It does not have an easy explanation from field theory. So if a field theory tries to explain this, they will have a difficulty explaining why lambda does not go like the cutoff to the 10 rather than the light modes. So the light modes play the role of the cutoff, not the heavy modes. Surprisingly, and that's the main key point. So that was a kind of an explanation that the distance conjecture, the generalized distance conjecture, offers a solution to the cosmological constant problem. That is lambda. When we say m goes like lambda to some power, it is in a sense a solution to the distance to the cosmological constant problem, because as lambda is pegged to the small mass tower. Okay. So now we still have to find what is alpha for our universe. I claim that alpha is less than a half. Why is it less than a half? Well, this is because of the Higuchi bound. Higuchi bound tells you that for de Sitter space, the unitarity constraints on a spin-2 particle, which includes states of this tower, gives you a band for which the mass should be bigger than lambda to the 1/2. That means the alpha should be less than or equal to a half, because lambda is less than 1. So alpha is less than or equal to a half. Now, these tower of states are lightly coupled. That's part of the distance conjecture, tells you that they're given by weakly coupled states. So there would be diagrams that they would contribute to the vacuum diagrams. Because they are weakly coupled, you should allow them to go on loops. So there would be contributions, at least of the form of m to the power of d. Maybe plus other things, but at least it will include this. However, if the alpha is less than, if alpha were less than 1/d, then that means these contributions should have been canceled somehow. But this is not true if you have no supersymmetry or anything else. So generally, you don't expect this to be possible. So the most natural expectation is that this is equal to bounded by 1/d. And this is what we're going to assume. So alpha is bounded between a half and 1/d, and m is going to be the tower of those states. Okay, so now what we want to apply to our universe. I claim that we are now ready to make predictions about our universe And indeed, I claim that, so therefore in our universe, D is 4, so M is basically scales, there's a tower of states whose scales like lambda to the alpha, where alpha is of the between 1/2 and 1/4. Now, the question is, what is this tower? Is it a string tower or KK tower? Which kind of tower do we get, string or KK? I claim it cannot be a string tower. Not possible. Why is that? Well, what are the limits we're getting for this tower? What are the masses of this tower? On the one end, when alpha is 1/2, the mass of this is the Hubble scale, which is a very small mass. Basically the Hubble mass. On the other hand, when alpha is 1/4, this is of the order of a milli-electron volts or smaller, around milli-electron volts. So the mass range is very small. This will be the scale of the string tower. So if you have a string whose scale is this small, the gravity will be badly broken in this scale to give you much more higher order corrections that we would have observed by now. So therefore, it cannot be a string tower. We have ruled this out as a possibility. It has to be a KK tower. That means that we are in 4 dimension, but there must be some extra dimensions which are getting big. That's the KK tower, which are getting large. And the mass should give you an expectation of what is the 1 over the length of the extra dimension. Okay, so now we can ask the following question. Indeed, if you have a KK tower, you start with a higher dimensional theory. Let's say in dimension n plus 4, you go from 4 dimension, you have n extra dimension. You start with a theory up here, which has the Einstein term. Let me call it the Planck in higher dimension, m hat Planck. And you put it down to, and you get an effective theory in the lower dimension, which is the m Planck to some power here, I meant, which is dn plus 2. And here would be m Planck squared. There's a volume factor between them. So when you put that volume factor around, you find that this makes a prediction that m Planck to the power of m plus 2 is equal to m Planck squared in 4 dimension times m to the power of n. In other words, the Planck mass in the higher dimensional theory, let me set the Planck in 4 dimension, let me set it equal to 1. It says Planck mass in the higher dimensional theory scales like m to the power of n over m plus 2. So then it turns out that, and we are saying that what is the values of m? We have to know what the values of m could be. We already said that lambda to the 1/2, m is bounded by lambda to the 1/2 to lambda to 1/4. Sorry, bigger than this, the other way. So the range for lambda, the exponent was that. So in other words, m is bigger than lambda to the 1/2, but less than lambda to the 1/4. But it turns out that the Newton's law have been checked up to of the order of lambda to the 1/4. Namely, it has been checked up to about 30 or so micron, which in the length scale is given by this. Therefore, we learned that the only possibility for the exponent is that the tower is driven by the last exponent, 1/4. You have to be very close to the 1/4 value. Otherwise, 1 over r squared force law would have been violated. So you have no choice. So you have extra dimensions, and we don't know how many, but the length scale of it should be of the order of lambda to the 1/4 inverse. And that's about 10 micron or something. How many n's do we get? Well, we have this relation that the higher dimensional Planck mass goes like m to the n over m plus 2. And now we know what m is. M is lambda to the 1/4. You plug it into here, and you find that for n bigger than 2, it doesn't work. Namely, you find that for n bigger than 2, the higher dimensional Planck mass is less than TeV. But we know in accelerator physics, up to TeV we have checked, and there are no black hole productions in the accelerators, which would have happened if the higher dimensional Planck was less than TeV. So that means it cannot be more than more than 2. So it could only be 1 or 2 extra dimensions. The 2 extra dimension is ruled out by different reasoning. If you compute it for 2 extra dimensions, you find m Planck is of order of TeV. So this is still not ruled out, because we could have some order 1 factors wiggle room, which could potentially say that we're still about to see it in accelerator physics. But there's something else rules this out. It turns out that in the context of supernova, you create neutron stars, and you create, in the process of creating neutron star, you create the KK modes with the n equal to 2. And when the KK modes decay, they heat up the neutron star, and that heating up will be inconsistent with observations for n equals to 2. And the only one which is not inconsistent one is the n equals to 1. The n equals to 1 is consistent with observations, and it gives you higher dimensional Planck scale of the order of 10 to the 10 GeV. So this is the only possibility, that we have 1 extra dimension of the scale of micron, or about 10 micron or so, with a higher dimensional Planck scale of the order of 10 to the 10 GeV. So we are making a prediction that if R is much, much less than 1 micron or smaller, then the 1 over R squared gravitational force law, this is the length scale, 1 over R squared gravitational law should become 1 over R cubed, should transfer over to 1 over R cubed, because we open up 1 more dimension. And this is being measured actually as we speak. Adelberger and his team are trying to actually compute to improve their bound of 30 micron, push it down to 10 micron.
Can I ask a question, Kundan?
Yes.
So if the effective extra dimension is n equal to 1, could you comment on how we should view the other extra dimension if we try to realize it in string theory?
They should be smaller. In other words, when I say 1 extra dimension, I don't mean just 1 line. It could be like ellipsoidal. In other words, the extra dimensions are just small, the other ones.
Much smaller than the 1
Yes.
extra dimension.
Yes.
Okay, thank you.
There's one of them which is extreme.
Okay, thanks.
Okay, now I come, see, I'm a bit, how much time do I have?
You have 80 minutes.
I have 8 minutes, okay. I have to rush through this then. So we have 1 extra dimension. I'm drawing it like this. And you could ask, where do we get our standard model? If the standard model lived on the whole 5 extra dimension, you'll be in trouble. Because if the standard model was an extra dimension, then you get the KK modes of the standard model. You got copies with electroweak gauge bosons of n equal to 0 mode, but you also have all these oscillator modes with 1 milli-electron volt, 2 milli-electron volts, and so on. You get a huge tower of copies of electron, quarks, etc. That can't happen. Therefore, this is not possible. The way it should happen is that our universe is coming from a localized brane. The standard model should come from a localized brane in the extra dimension. Otherwise, you'll be in trouble. Finally, I want to talk about the cosmology of this model. So, and this is related to the following question. We have dark energy, which predicts a tower of light states. Where is this tower? Why haven't we seen it? On the other hand, there is dark matter, and we haven't seen it. We know it exists, but we don't know exactly what it is. I'm going to argue that these are the same. In other words, this distance conjecture unifies the dark energy and dark matter into one entity. The dark energy implies the dark matter and nature of dark matter. So they actually connects the two facts. The two dark features are connected. The dark energy and dark matter are two sides of the same coin. So I will try to explain how this would work. So I will be brief because unfortunately I don't have too much time, but the idea is the following. For the cosmology to work, you cannot have the whole 5-dimension be in thermal equilibrium at the time of Big Bang nucleosynthesis. So at the temperature of around 1 MeV, we know that Big Bang nucleosynthesis takes place. So at least our brain should be at that temperature. But if the bulk was at that temperature also, then you get the number of light species since this has electron volt scale, you have a huge number of light modes in addition to the Big Bang nucleosynthesis models, and that would be wrong. The N effective we know is about 3, the number of effective degrees of freedom, which we know is related to the number of neutrinos, and you cannot have a huge number of things in the bulk. So basically this tells you that at some point, the main temperature or the main energy should be localized in the bulk modes, in the brain modes on the standard model. So we start with that, with some initial temperature in the bulk, in the brain, and you want to know what happens then. So if you start with that, what's going to happen is that this is going to emit graviton modes into the bulk. Why is that? Well, you have no choice because of the universality of Einstein's equivalence principle. It tells you that there's a coupling to gravitational modes. Namely, you have a G mu nu of the 5D theory, which couples to the T mu nu of the 4D brain when you restrict the G mu nu to be at the origin, if you view this point at the origin. If you have this some x5 and you view this as the origin, so you put the gravitational mode at the origin and it couples to the energy momentum tensor on the brain. That means our standard model energy momentum tensor. And the G mu nu of the 5D theory should be viewed as G mu nu of the KK modes of the graviton times phi n, where the phi n are the gravitational modes, the gravitational eigenmodes, KK modes, and you evaluate at the origin, which means that you have some universal factor here, which is 1 over the square root of the length of the extra dimension. And so from this, you get a coupling of G mu nu to the T mu nu of the standard model fields universally. So we now know that the standard model fields will create gravitons in the bulk universally. So you can make a prediction of how much they create. So you use that and you end up getting a creation of the matter in the form of the KK tower. So you ask, is there any initial temperature for which the matter that you get gives us the dark matter we want in our universe? And you find indeed that's the case. You find that if the T initial is of the order of a few GeV, like 5 GeV or so, then the matter that this creates will start with something of the mode number in the KK tower of the order of around 10 to the 9, which is very, very massive tower here. You have all of these, but bulk of the energy is going to be in the 10 to the 9. But this is just creating the matter on the in the form of the KK modes of the graviton. But then the universe continues to expand, and the temperature of our brain becomes down. So you go from you're still in the radiation mode, but the temperature goes down. But it turns out that the distribution of this dark matter, which is not in thermal equilibrium with the standard model field because it's just created from them, scales lower with temperature. So they lose less mass. And therefore, after a while, they become dominant. And it turns out that precisely at the value of the 5 GeV, if you start with this 5 GeV, they become dominant just before the matter radiation, just before the dark energy takes over. So this exactly works the way we want, including the fact that the modes of the KK tower actually decay. But actually, we can do better. We can actually predict the T initial. And this will lead to the solution of the coincidence problem. In other words, we don't have to put in by hand what is T initial. We can get an estimate of T initial. You see, the modes on our brain should have stabilized before we get to the cosmology. But the modes have a decay constant. Oops. The modes decay, there's a rate of decay which gives you by the mass of the fields, the dilation modes of the brain and so on, divided by m Planck squared. This you can expect because of the fact that these moduli fields are gravitationally coupled, so there's going to be a factor of 1 over m Planck in their coupling, and so the rate will go like 1 over m Planck squared, and by dimensional analysis should be m phi cubed, where the m is the mass of them. So this should be the rate. But the rate of the decay should have been bigger than the Hubble rate, which is lambda to 1/2. Why is that? Because if they didn't decay, if they did not decay, by the time you get to the Hubble scale, you will never have a de Sitter space. You have to have decay by that time. Otherwise, the de Sitter space will disappear by itself, according to the TCC. Therefore, we learned that the mass of these states should be bigger than lambda to the 1/6, or equal in the Planck units. I'm putting m Planck to 1. On the other hand, the initial temperature should be less than m phi, because otherwise, if you have a higher temperature than m phi, they will excite them. And so you're not in a four-dimensional situation. So therefore, a safe initial temperature is of the order of lambda to the 1/6 because of this inequality. And lambda to the 1/6 is of the order of GeV. So we can make a prediction of the order of the GeV for the initial temperature, which is lambda to the 1/6. Incidentally, this is close to the Higgs mass. So the hierarchy could potentially, electroweak hierarchy, could be related to the fact that this mode scales like lambda to 1/6. In other words, we could be getting also a unification of all hierarchies in terms of one extreme small value, which is the dark energy. So from the smallness of lambda, we can explain potentially why the weak scale is small by power of lambda. And this begins to sound like the question, a resolution to the question that Dirac was asking, the question of large numbers. Why do they seem to be related to powers of each other? And this in some sense is related to the distance conjecture, the fact that the distance is logarithmic in lambda. And therefore, this power law behavior is coming really from that feature. And we are getting an explanation of all these scales. So I think I have unfortunately rushed a little bit, but let me just say that this gives you the dark matter that we started, which of the order of GeV, decays down until you get to the mass of the dark matter today of the order of 100 keV or so, kilo electron volt. The fact that it's weakly coupled is guaranteed because it's gravitational. So it behaves in some ways like the cold dark matter, but not quite. Because when it decays, it gives you a kick to the dark matter. And the kick to the dark matter will give you a different structure formation. And it's actually very interesting to see which features you get from this kick that they get from this decays, and we're currently studying it. I think I've run over my time, so I think I should stop. Thank you very much.
Thank you very much. Any question?
Can I start by asking something a bit general? So you have made great predictions and insights from these swampland things, but I wonder if you're going to actually realize that from string compactification, which general direction do you think should be pursued more? Like, should we proceed this existing landscape program like KKLT, or do you have other things in mind? If you can share your insight, it will be very helpful.
Well, I wish I had a good answer to your question. I don't. Of course, it's a very important question. We should try to construct such thing in string theory. You see, what we know is that it cannot be the extreme far corner of the parameter space, but it should be not too far from it either, because I'm using the parameters for large distance. So we should be very close to here. But what form of it is it? Is it going to be like this? Or is it going to be maybe going to go slow slope, continue down? I don't know. Or it could potentially be even a metastable up state, In fact, that's another possibility. We don't know if that's the case or not. You can be on the top on the metastable point.
So, for instance, you don't think it's in the very strongly coupled regime?
No.
In which case,
In
it would
some
be very
sense, we should
difficult.
be in the weakly coupled regime. The fact that lambda is small means that even though we are not in the infinitely weak coupled regime, we are sufficiently close to it.
Okay.
Now, people have tried to use this, for example, KKLT, and the large volume scenarios are precisely trying to exploit this possibility that we are in a weak coupling point, but not infinitely weak coupling point. So this is morely in that same regime.
Because they need some
my only
non-perturbative
issue is that
ingredients.
I still have issues with the actual implementation of those scenarios, but the range of parameters they're at is exactly where we want to end up in this scenario.
Okay, yeah. Thank you.
Right.
So I'm wondering
Well,
how robust.
Can I ask a question?
Yes.
Well, in inflation theory, well, the potential seems to be concave. I mean, convex potential seems to be ruled out. Do you have any idea why it is the case?
Inflation theory. Inflation has a large number of issues with the swampland issues. I can explain many more of them. For example, the distance conjecture has a slight tension with the fact that if you go a large distance on an inflaton field, you get light states. So there are these issues that could potentially hit you in the context of inflation and other things. So I mean, there are too many problems. Now, you could ask me, if I have problems with inflation, what am I going to say about early universe? What gave us the homogeneity? What gave us all the things that we know about inflation? Well, I should say that in this case, we have to know that the main accomplishment for inflation is that it gives you essentially a homogeneous universe with a slight deviation from scale invariance, tilted in some direction. That's the main input that we get from inflation. The rest follows from that. However, these features actually can also be implemented very easily from the ideas from string dualities. Let me explain how. See, if you take our universe and take it back, the temperature is getting larger and larger. You can push it further and further into a regime where you say, this is an extreme parameter. After all, this is like e to the, if you go to the Euclidean description of temperature, you get e to the minus beta h, and you're talking about the limit as temperature goes to very, very large values, as beta goes to 0. Beta goes to 0 is like an extra circle, thermal circle going to 0 size. And that is one of the examples of the infinite distance conjecture, that you should get some new degrees of freedom, some light degrees of freedom should come to play. In other words, the effective field theory should break down at the early universe time. Inflation tries to say that, no, we can avoid it. But the most natural solution in string theory is actually that our picture, the effective field theory we are dealing with, breaks down. What that means is that we had other degrees of freedom in the early universe that were much lighter than us, and we were heavy. And when it came to us, they become the heavy guys, and we became the light, and they decayed to us. But when they decay to us homogeneously because they're non-local relative to us. For example, like T-duality, you're having these other extended modes which are non-local relative to us, and therefore they will automatically give rise to a homogeneous universe when they decay. The issue of horizon problem in the context of usual cosmology of how could it be that you have two different rays from two different directions which have the same temperature even though they are not in causal contact, is that the notion of non-locality emerges automatically because our description of the universe with our degrees of freedom is not local. For example, T-duality is not a local operation. So the most natural solution to the early universe in the context of string theory is a dual formulation, which we don't know exactly what it is. It could be something like a T-duality, but it's not. It is not. We don't need something like as exotic as inflation. You need. We are automatically forced from ideas from string theory to look for dual formulation. We can even get the tilt in the right direction using unitarity ideas if we replace the early universe, this decay process, by topological phase of gravity, which we studied in some paper recently.
Thank you very much.
So I'm wondering how robust the predictions are. For example, lambda to the 1/3 and lambda to the 1/4 differ by
I think 5 orders of magnitude or so.
Right. So lambda to the 1/3, it cannot be lambda to the 1/3, because if you had lambda to the 1/3, you would get contradictions with 1 over r squared experiment. So lambda to the 1/4 is the regime that you have to be in, very close to lambda to 1/4.
Sure.
You can be maybe slightly less than 1/4. It could be, you could ask whether it could be lambda to 1/5,
Right.
but the 1/3 is not possible.
Okay.
Now, I tried to argue why 1/4 was natural, but there's an overall coefficient that we do not know. But the coefficient should be such that it doesn't change the exponent, because that's a different. That would say that the coefficient, which the one loop contribution of running these light modes in the loops don't give you the right value, and that's strange. So therefore, this cannot be 1/5 either. You will have a lambda to 1/4, which is more dominant.
Okay, so you would say the exponent is fixed, but certainly the coefficient is free at this point.
That's right, but the coefficient should be not so different to make this 1/4 to behave like 1/5, and that gives you an uncertainty for what the value of lambda, the length is. So that gives you the mass of this, which is the length of the extra kk modes, and from that we learned that the length modes should be something between 0.1 micron to 10 micron roughly. This is the range. This is kind of a ballpark estimate by looking at variation of the exponent here.
Okay, thank you.
Yeah.
Hi, Kerman. Thanks for the great lectures. Question about this idea that dark matter is this set of KK modes. Can you say more about why I might expect these KK modes to be dark?
When you say dark, you have to, KK modes are basically gravitons. They're just higher KK modes of graviton. The 0 mode is our graviton. The higher mode is what we're talking about. And graviton interacts gravitationally, which is weak. So therefore they are dark in that sense. So
Good.
It's perfect. Without our putting it, it's automatically dark.
Good. So would you predict that they are not weakly interacting? Like they aren't WIMPs? They don't interact?
They are super weakly. In other words, they are much more than weakly.
Sorry, I mean interacting.
So in other words, they are not direct detectable.
Okay, good. So you would predict that they don't interact via the weak force, for example.
They can only be seen gravitationally because they're gravitons.
Very good. Thanks.
Yeah. So the nice thing about this is that people, when they talk about dark matter, they have to input something by hand, like you have extra stable particle or this and that. Here, we were forced to do this. We didn't have any choice. So this single idea solves or connects many different ideas. It connects a natural candidate for dark matter. It tells you the extra dimension are useful for solving it, and the extremeness of the dark energy being related to the extra dimension is natural. And so it puts together a lot of facts together, and surprisingly, it's not ruled out. In other words, it could have easily been ruled out, and we have only been cornered to one possibility with one extra dimension with some particular scale, which is quite surprising that hasn't been ruled out. So we are very excited about this possibility.
So I have a general question about the whole program. So when you talk about starting from field theory and then coupling it to gravity, do you have in mind of weakly coupled Einstein gravity or even beyond?
No, I was talking about something which the infrared looks like Einstein gravity.
Oh, Einstein gravity.
Yeah, you could have some more exotic, like higher spin ones. I was not talking about that.
Okay.
So I have one question. So you mentioned about the Higuchi bound of the mass of spin to particles in this in distance contexture. So are there always spin to particles in the light tower of light particles in the distance contexture?
Yes, the reason is that we said that the tower is either the KK tower or the string tower. KK tower is the Kaluza-Klein tower, which always includes a massive gravitons, and graviton is spin 2. And the string tower always includes many higher spins, including spin 2 and higher.
Okay, thank you.
Yeah.
Yeah, a question from Zoom. Can you explain more about the dark matter mass at 100 keV you mentioned at the end? How is it derived?
Yes. So a good question. So I told you that there's a tower of this KK tower, and the initial temperature was GeV. So you go to the mode number roughly like 10 to the 9 or even higher, but they start decaying. There are many decay channels, but the decays are, each decay factor is gravitational, so they're very slow. Even though we usually think about KK modes as unstable, and that's true, the decay is very slow because they're suppressed by factors of 1/n Planck. So this fact allows them to be more or less stable, but that's not true. Their mass shifts down and goes down. So you have to estimate the decay rate of these. And it's basically, you just see how many channels are available. And in addition, you have to assume what is the violation number in the quantum number. So in other words, there's the KK mode number. And if it was exactly a circle, if the extra dimension was really a circle, there would be no violation. This would be 0. But if it's not a circle, this is not exactly 0. And it could be some order 1 number, like delta n is between, let's say, 1 and 10. So you can assume something of order 1 or 10 or whatnot. And using this, you can get an estimate for the rate of decay. And from this, you can see how the tower rate changes, the mass of the tower changes. And you find that the mass of the dark matter scales like 1/10 the time to the power of 2/7. And so you can just do this and compute it. And that's how we find the mass of the dark matter today. In fact, it had to become lighter. If the mass of the dark matter had stayed around the GeV, then it would have been contradiction with the CMB spectrum. And the reason for that is that the dark matter, because of the universal coupling G mu nu n to the energy momentum tensor of the standard model, they can decay to photons or other dark matter stuff. So you have a mode like a dark graviton is decaying to 2 photons. And this decay rate would be too high if the mass is 10 to the 9 GeV at the time of CMB. So at the time of CMB, their mass should be sufficiently lower, and in fact should be less than MeV. And indeed, it drops down exactly at the right time to avoid this, miraculously. So in other words, this whole thing as if it's built to avoid all the contradictions. So everything we are doing somehow fits together without our working too hard. And using this, you get a mass today of the order of, I don't know, we have, it depends on exactly what parameters you choose for delta n and extra dimension of the order of a few hundred keV, all the way up to 1 MeV, but no more.
Okay, another question from June. What kind of mechanism do you have in mind when you say the standard model is localized in the extra dark dimension?
Well, the standard model, as we know in string theory, the gauge theories naturally live on d-branes. And d-branes do not live on the whole bulk space. They are usually on a subspace. So this is very natural. Like in F theory, we have these 7 branes that the matter lives on. So I'm envisioning something like in F theory.
Any other question?
It's a general question for supplement program. Using holography, we can consider some holographic dual version of swampland program. Then, do you have any example of CFTs which cannot survive some in dualized version of swampland program?
I'm not sure I completely understood your question, but if you, I think you were just saying that there's the swampland version in the context of holography, which
Yes.
is true, because you could naively think that every conformal field theory with all the properties could appear, but crossing symmetries and consistency of conformal field theory are far more restrictive, and they will put restrictions that are not obvious a priori. And so indeed, that's the case. And people have been trying to find these restrictions, and they know that there are restrictions, and we don't know the answer to that. We expect that in the context of ADS, precisely those bootstrap methods, perhaps, or ideas coming from the constructions of unitary theories, will automatically lead to swampland conditions for ADS. So I think the two programs should be related, of course.
Yeah, thank you.
Thank you.
Yeah,
I think it's one of the most exciting directions to use that.
Question from June. what could explain the Yukawa coupling textures?
I didn't describe it in this talk, but there were some ideas along these lines having to do with the F theory realization. This is in a paper we did like about 10, 15 years ago. And the idea there is, so I'm just going to tell you since you asked, but it's not related to my discussion here. When you talk about the Yukawa coupling, it came from intersection of branes. And so if you have intersection of branes there, it turns out that the different generation correspond to different excitations, which different zero modes of the Dirac operator on each of these surfaces. So if you look at the zero modes of the Dirac operator, the interaction mechanism only comes from one point, so it has rank one. That tells you that to the leading order, the Yukawa coupling, or more precisely, the mass texture, is of the form 1 and 0, 0. So in other words, there should be one heavy one, and the rest should be almost massless. And this is already very close to the standard model situation where the top quark mass is heavy and the other ones are almost light, massless in comparison. But actually, we continued this and we found not only this is right like one, but we also found corrections having to do with the powers of grand unified coupling constant. And we kind of estimated these exponents, what they are, and we kind of gave a heuristic explanation of the texture. Because of the correction, instead of the overlap, we get some corrections to the overlap formula. This is in some way the realization in string theory of Frogat-Nielsen mechanism.
Yeah, so this is a question I think was asked before. So this program where you found that n equal to 1 or 2, the maximum number of the extra dimensions that you possibly can have from this program, it does not contradict the fact that in string theory you would need 10 dimensions somehow.
Sorry, maximum number of large dimensions I was talking about. I think this question, I think Siok already raised.
Yeah.
I was not talking about all dimension, but large dimension. We said there's one large dimension.
I see. So the statement is there, at most there can be one large dimension. There can be numerous.
One mesoscopic dimension you could call micron.
I see. Okay, thank you.
Related question. So can you also estimate the scale of other extra dimensions which is much smaller than this mesoscopic dimension?
No, we cannot.
Oh, okay, I see.
It shouldn't be too much smaller than, too much bigger than in Planck though. In other words, it shouldn't affect our analysis.
Any other question? Okay, if there is no more question, let's thank Kumnan again for his wonderful series of talks. So this is Kumnan's last lecture. So thank you so much, Kumnan.
Thank you. I really enjoyed it, and I hope you enjoy the rest of the lectures there. Thank you, everybody.
Yeah, thank you.
Have a good time. Bye-bye.
Yeah, bye. Good night.
Night.
Thank you very much.
Yeah, yeah. Can you hear me? Looks good. Uh, no, no, no. Just checking. No. 50. Okay. Uh, um. So yeah, maybe yeah, yeah. That might be better. Yes. Yeah.
This mic is good, but that means this microphone should be very close to your mouth. So then,
Yeah. It should be working.
yeah, it works,
Yeah.
but it's better to if you mic it. Can I?
Yeah.
Only close
Yeah.
to
Yeah.
your mouth.
Yeah.
So they said it's good
Uh.
mic need to such a close distance. So yeah.
Yeah. Yeah. Yep. Oh. Can I put off my mask? Oh yeah. During the lecture. Yeah. Can I put off my mask or should I? Okay. Mhm. Okay. Thanks. Maybe it's hot. Where did I put my iPad? Oh, what? Sorry. Strange. No, no, sorry. This is not my. This is not my. Yeah. Okay. Just.
야, 이제 시작이에요. 근데 왜 안 들어오죠, 사람들? Restarting 1 minute. 아니, 괜찮을 것 같아요. Okay, let's begin the second session of today's program. So we will start a new series of lectures by Professor Kantaro Omori from University of Tokyo. He will give us the first lecture today about non-invertible symmetries in 3+1 dimensions. Yes, please.
Thanks for the introduction, and also thanks for the invitation of giving a lecture in this wonderful venue. And I first start thanking for also thank organizers for running this wonderful school. So let's start. So my talk is about non-invertible symmetries, and the emphasis is on that it exists in our dimension, the 3+1 dimensions. But I found that most of my lecture practically will be about 1+1 dimensions, which because it is simpler to explain. Okay, but of course I also introduce the examples in 3+1 dimensions. And the plan. Okay, so this talk will be about some generalization of symmetry, which is called a non-invertible symmetry. And the plan of this talk is here. So first, I start from introduction. Then I will talk about the relationship between the symmetry and the topological operators. Okay, so this part will be very basic. Then I will give two constructions of this thing. One is called house space gauging. The other is related to Lebesgue anomaly. Okay, and the two are related. Okay, so let me start from the introduction. Okay, so this talk is about symmetry. Okay, and the symmetry is one of the guiding principles in physics, and I'm sure that all of you use symmetry in one way or another in your research life. Okay, so why are we so interested in symmetry? Why is it useful? Okay, so So sometimes it explains some surprising thing. Okay, so some surprising. So in history of physics, it often happens that some experiment or other method find some surprising coincidence or cancellation of some physical quantity, and that is later explained by the symmetry. Okay, and also it organizes, particularly in quantum physics, it's known that the symmetry organizes states and operators into representation. Okay, and okay, of course this is correlated with the first line, and that's how we use the symmetry. Okay, so in quantum field theory, these two things comes from Ward Takahashi identity. Okay, So so the non-invertible symmetry that I want to talk about is a form of generalized symmetry. Okay, and so from that perspective, it's natural to defining generalized symmetry by generalized Ward-Takahashi identity. Okay, and this generalized Ward-Takahashi identity comes from topological operators. Okay. So the message here is that knowing about the topological operators that I'm going to talk about it is, gives rise to the generalized kind of Takahashi identity. And then you can regard that either of generalized Takahashi identity or topological operator itself as generalized symmetry. Okay. Okay, so that's how we get the generalized symmetry. Okay. So recent development in these 1 or 2 years is to finding examples, numerous examples of so-called non-invertible symmetry. Okay, in dimensions greater than 2. Okay, so this kind of symmetry is essentially known in 2 dimensions. I mean 1 plus 1 for a long time. Okay, but recently we are finding many examples in D plus D greater than 2 and in particular D equals to 4. And that some of the examples I want to talk about. Okay, so this is the introduction. Any question? Okay. So symmetry and topological operator. So I start from the conventional symmetry, and okay, that is in any QFT textbook. And so first thing I want to emphasize is that if you have a conventional symmetry, then it gives rise to a set of topological operator. Okay, for each, so conventional symmetry is described by a group. So G is your symmetry group, and for each element of your group, there's an associated topological operator. Okay. So that's first thing to see, and that's the basis of all of the development of about generalized symmetry. Okay, so for simplicity, let's assume that G is continuous. Later, I remove that constraint, but for now, I assume that the G is continuous, and even, well, for example, just the U1. Then, so let's say we have some field phi, and acted by a usual way, and as a and I denote the field or operator acted by a symmetry element alpha or G as the phi to alpha. Okay. And of course we assume that the system has this symmetry, so the action is invariant under the symmetry action on the field. Okay, so then let us first recall how to derive the Wald-Takahashi identity. Okay, so I assume that all of you have learned about it. So I go quickly. The consider operator of which is here I assume this is a product of local operators. Okay, so O is just a collective notation of the product of local operators. And so each local operator has a charge, okay, or in general representation. But let's work with the U1 case. Then there are associated charge. Okay. Obviously, if O is O1 is a phi x. For example, no, sorry, phi x to q1 or something like that. Okay. Okay, so this I just rewrite this as a path integral. O of phi. And okay, so here I do the change of variable to phi alpha. Okay, so this is change of variable. So I have done nothing, not even having used the symmetry. Okay. Then I use symmetry. Now for the but here so I should have said. So of course this equality holds for alpha constant. Okay. So the point here is from that definition of symmetry. It seems that this alpha constant case is important, but in QFT context, actually, it's important that we can promote this alpha to a non-constant function. So here we do not assume alpha to be constant, but rather a function. Okay, so in such case, sorry for going back. So alpha non-constant. Oh, okay, that's good. There's a correction. Okay, but I've said that this S is invariant under when alpha is constant. So this correction has to be proportional to derivative of alpha. Okay, so I can, so first order, this should look like this. There's some vector j mu and contracted with the derivative of alpha. Okay. Well, of course, I'm assuming the relativistic symmetry and order of alpha squared. Well, this means order. Okay. And of course, this is called Nater current. I should put parentheses here. So I substitute it here. Okay, so here I use the symmetry property of the action. And no, sorry, partial mu alpha j mu. Okay. And some higher order correction. Then it also affects this part. But here I assume that this O is a product of local operators. So you pick a phase and just that. Okay. So alpha is not constant, so depending on the position of your local operator, it can get a different phase here. Now I have to assume, or here I just assume that symmetry is non-anomalous, namely this measure is symmetry invariant. I will come back to this point later in the lecture, but here I just assume that it's non-anomalous. So this is a non-anomalous condition. Okay. So this is the basic equation. Let me call this equation star. Okay, so we started from the operator and do the symmetry transformation with the non-constant alpha. Just that. Sorry. Oh, yeah.
Under any alpha of x, Not just. You assume the measure is invariant under any transformation alpha of x, right?
Oh yeah, any.
Not only
I
the
mean,
global.
not just global, but yes, any function alpha. Yes.
Yeah, so for example, in that last equation on that board, I could possibly write some other terms, like maybe, say, the Laplacian acting on alpha times some scalar. Why would I not write that term?
Sorry. Oh, so you, let's say,
yeah, times
this
some
kind of, yeah,
some
okay,
scalar
okay,
field.
okay. Let me see. So, just by saying that, good. Well, I mean, I can always, so if you have this,
Mhm.
then like times some other operator.
Yeah.
You should do integration by parts. Okay, and do this, and then this is a part of J. So the form of this, the first order in alpha, it should be some differential operator made of partial mu, and then some other operator.
I see.
Okay, but I do the integration by parts and put every derivative other than one to here.
I see. Okay. So you're saying this is perfectly general?
Yes.
Okay.
Of course, I'm assuming the relativistic symmetry. So without that, there can be many possibilities, and that's one interesting recent development about the subsystem symmetry. But I'm not going to talk about it in this lecture. Okay. Good. Okay, so the usual form of what Kahashi identity, and about the correlation function can be derived from the equation star by setting alpha to be proportional to delta function. Okay. So set this, and so epsilon is an infinitesimal number. Okay, and so what do you get? So we ignore here. Here we just get, because it's a delta function, and I also do the integration by parts. Okay, so this thing. Okay, and this is delta function, so I get the insertion of derivative of J. So the O is so that I actually, oh yeah, okay. So this part cancels. My lecture note says something wrong. Sorry, completely wrong. So I'm worrying about the sign. Okay, but let me keep going. Epsilon Qi delta x0 sxi times, well, okay. So the zeroth order part just cancels, and we get this. And that's the, there should be minus sign here. Okay, yes. I think this is correct. So this equals that. So this is the Takahashi identity. Okay, so it says that, okay, classically this J is divergence-less, which is Natal's theorem. Quantumly, if you have operator insertion, then there is there's a constant point correction to that conservation law proportional to delta function and the charge of the operator. Okay, remember that I assume that this is just product of local operators. Okay. So sorry. So before saying that, I want to emphasize that in this derivation, it was important that alpha is we could take that alpha is non-constant function. In other words, we know how to do the symmetry transformation point by point. And not just how to do the symmetry transformation on the space-time as a whole, but so essentially we assume that this symmetry transformation is locally done. Okay, so this alpha. Okay. Sorry. So this is, for example, we assume that this locally done, and this action is not like involving some integral over nothing. So it's locally defined, and therefore we could utilize the such symmetry transformation with the symmetry parameter varying in position. Okay, so this locality is very important. Okay. Okay. So so far so good. Any question? Okay.
Boundary terms. You are not worrying about such boundary term?
So here, okay, yeah. So yes, so sometimes funny thing can happen if you take alpha to be some winding mode, say around some space-time, some non-trivial space-time with non-trivial topology. So that's a form of anomaly. So that's one way of detecting a particular type of anomaly. And so here I'm not having into that detail. Okay, so so this Takahashi identity, assuming that the absence of this non-perturbative anomaly, then the Takahashi identity is just come from considering this kind of delta function configuration. Yes. 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 Sorry, would you get the mic?
For symmetry with the Hofstad anomalies, do we still have word Takahashi identities?
Oh yeah, so just having to filter anomaly. Yes. So I assume this just for the simplicity, and you get the in general anomaly give you the correction here, and so you have to put the correction in here, but just so if you know how the measure transforms, then you know how to modify the word Takahashi identity.
Okay, thank you.
Yeah. Okay, good. Okay, so this is good, but this is only for the continuous symmetry. And for the latter purpose, it's very useful to try to generalize this to a finite symmetry case. Okay, it's for the infinitesimal symmetry because it's here I put the alpha to be infinitesimal, but for a finite symmetry, you cannot do that. Okay, and finite symmetry. Oh yeah. So sorry, I might not erase this. So I erase this here. Okay, so instead of taking a delta function times infinitesimal number, we can take another function. Okay, so this is of the finite D identity. So here I still assuming the U1 symmetry, but I'm writing the slightly different version of what Takahashi identity that can be directly generalized to finite symmetry case. Okay, so to do that, I instead of taking a delta function, I take this function where this alpha 0 is some finite number, so this is 0, and so this is x, and V is some region, codimension 0 region of space-time. And so is just we have some V region, and this function takes 0 outside of V and alpha not inside V. Okay, just that. Okay, so then from star, I formally apply.
Can I ask you a question?
Yes.
So I know the subtlety of the derivation of current conservation for global symmetry, but I think that it is nevertheless very confusing to me that without assuming that the symmetry is a local, we don't have any, the conservation law. That is very confusing, I guess. And because we know that now, global symmetry has a conservation, but local symmetry doesn't have any conservation law because that's not a symmetry.
So I'm okay. I should emphasize that I'm talking about the global symmetry. So the global symmetry versus local symmetry is very, in hindsight, in my opinion, very confusing namings. And I should So I think we should be calling local symmetry, but we should call, I cannot say in good English, but so I've been talking about what's called global symmetry, but I'm emphasizing that symmetry transformation itself, we actually assume that is defined locally. But I'm not saying that the action is invariant under such local symmetry action. Indeed, so I wrote so this is when alpha is non-constant, there's a correction, and the correction is very important. Okay, so that's nothing but the native charge, native current. Okay, so yeah, but I want to emphasize that we implicitly assume that the symmetry, even when we are talking about the global symmetry, the symmetry action is defined locally. And in the derivation of what Takahashi identity, that fact is actually very important. Okay. Yes.
It is just confusing just because that is the definition of a local phase transformation, not global.
Yeah, this is definition of local field transformation, but I'm not assuming the invariance of action under that. Okay, I only assume that the invariance of action is only for the constant alpha.
But by assuming that one, I guess that what can you say about the global symmetry? Because if we assume that it's global, then derivative of alpha is 0, and you still go back to the
yes
invariance of the action, and that's actually origin of the symmetry. So why we should talk about the local transformation?
Oh, so if let's say the point is that the field transformation is defined locally. So this is not like that. I don't know the more general form, but it might be like absurd, like random thing, like the y of phi y of some function of like I don't know, but like alpha or something, x y or something. Not like this complicated transformation, and you just do symmetry transformation point by point, and that fact gives us the natural notion of phi alpha with alpha non-constant. That's all I'm using.
Yeah, but I guess after your derivation of a one-point function case is, I guess, truly more confusing, because you really assuming that the alpha is a delta function, which is cannot be reduced to constant. So
would you say again
I think we can discuss later.
I can. Okay, let us talk later. Yeah, I think this is very confusing point about. Yes, I'm emphasizing the locality of the global symmetry in QFT, but I'm not saying that the symmetry is a so-called local symmetry.
Can I maybe ask a perhaps related question? So you're assuming that a global symmetry transformation can be promoted to certain local actions, set aside it's a symmetry or not. Could there be some subtle global symmetries which defy that? Which defy the natural extension of a local transformation, or maybe ambiguous or whatever? I don't have any example in mind, but
so well, I do not have neither in QFT, but the point. So yeah.
So here you.
So here. So we are saying that we are doing QFT and we know the notion of points.
Yeah.
And so then.
Yeah, but I'm just wondering whether there could be very subtle, I don't know, some global symmetry transformation of a field which might never accept natural localization of, I mean.
Well, I don't have any such kind of theorem, but I would say this is so yeah. So instead, if you are doing some matrix model, then where this notion of point or position is fuzzy, then you can say that if even the matrix model have a symmetry, then that's local. That's yeah.
Yeah, quick question then related to what I was asking before. So if you have a measure that is invariant under the global but not the local symmetry, would you? Is that something that happens? Do you assume that you absorb it in J somehow, the variation under the local?
So what is?
Yeah, my question is that I don't know if it happens in normal cases, but if you have the measure of phi to be invariant under the global symmetry, which is what you want, but not invariant under the local.
Oh, so
then can you absorb it in J, or is that something that happens?
So yeah. So in well, let's see. Yeah, here. Well, so this assumption may not hold, and well, yeah. So this assumption is not general true, and for non-local alpha, and so that's the classic case of anomaly. Just say having Kailov fermion, then.
But I thought, maybe I'm wrong, but I thought the anomaly would be if the measure is not invariant under the global symmetry, that you want it to be an actual symmetry. But I'm
if you...
if it's invariant under that, but not under the local transformation.
Oh, without... Well, there are several cases, but there's a case that without turning on the background, then the measure is invariant under the constant alpha in some, for the fifth anomaly case, it's. But if you turn on, so what often happens is that if you turn on the background for your symmetry, that I haven't done here, but if you turn on the background, like adding A, some classical field A and J, then sorry, I said something wrong. Oh yeah, but yes. Then this part becomes non-constant. Yes. Yes. Yeah. Fujikawa's calculation. This is non-constant. Yeah. So that I believe that's not for just doing the constant transformation. Sorry. I mean, yeah. Just for the fifth anomaly for the U one. Then without background, so for the fifth anomaly for the U1, the self anomaly, not the ABJ1, that mixed with the gauge symmetry that I'm going to talk about, but not for the self to fifth anomaly. Then without turning on this A, then the Takahashi identity applies as is. Okay. So Okay, so how many minutes?
You have 30 minutes.
30 minutes. Okay.
35 minutes.
35 minutes. Good, good, good. Okay, so I'm going to do the finite Takahashi identity, which is just yeah. So I set alpha here there to be this function instead of delta function, which and okay. So let me call this function to be alpha b of x. Okay, and alpha b, alpha b. Okay, so just formally, I define this. Define an operator u, alpha b, and dagger. I just put dagger here for the notational purpose, and so this part we just get so the O is the operator, the product of local operators, and of course the operator inside V gets acted. So this part xi is inside V, and qi alpha here I have alpha naught is a constant. So this is a constant, and okay. Okay, so what we get is, well, I moved this to here actually. So okay. Oh, correlation function. Maybe just O. Okay, so this operator U alpha B is the operator that computes the charges, okay, of the total charge inside this region V. Okay, and the point is that this alpha V, so S, we assume that the global symmetry invariance of the action, and that means that alpha V for the complement of V bar is the complement of V, is just the dagger of alpha V. Okay. In other words, if you do no, this is 1. So maybe I say inverse. So it's better to say inverse. Okay, so okay. So this means that U of alpha b depends on just the boundary and its orientation. Okay. And not so I rewrite so from now on I write this to be U of alpha naught depends on the boundary of V. Okay, and I do not explicitly write orientation, but that's also implicitly specified. Okay. Okay. So for U1, okay. So for U1, you can just explicitly compute the definition and this one depending on, and I also often write sigma 1 to this the boundary of region, which is codimension 1 surface in the spacetime. So here just the U alpha naught is just the integral of sorry, exponential of Nato church. This is called the Nato church. Defined on the arbitrary codimensional surface and the weight alpha naught. Okay, but that equation, this equation itself, maybe I write this double star. The double star is a finite version of what Takahashi identity works for discrete symmetry. Okay, so what is the content of this equation? So the content of this equation is that there is some operator which depends on which is defined on sigma 1, the codimension 1 surface, and okay, so this is U sigma 1 alpha. Okay, and so I'm just repeating, but so maybe I call this G. Okay, so G is that your for each element of G, for each element of your group G, there is a corresponding operator which is not local but defined on codimension 1 surface. Okay, I'm confused. No. Notation should be like this. Okay, sorry. Then, okay, and what this operator does is that the O3, O4, to act on the operators inside, let's say this operator inside on this sigma 1 surface with the group element G, like this. Or you can also shrink this operator towards the infinity. So if you do that, if you do that, this operator acts on outside of this region with the inverse action. Okay, but it also says that this operator is topological. In other words, you can deform it arbitrarily because what it does is just acting on the operator inside or outside. Okay, so you can deform it arbitrarily, like this, and this is too absurd. Sorry, but as long as this operator does not cross the local operator. Okay.
Discrete symmetry or works for also?
Works for any, yes, works for any. Any conventional symmetry.
What is the reason? Reason for discrete symmetry?
Reason for what? Why this works?
Yeah.
Well, I gave you the derivation, so.
But in my opinion, this kind of argument seems to work for also continuous symmetry, but continuous symmetry breakdown for this argument?
No. Works for any means any. Including continuous symmetry. Yes.
But also work
for discrete symmetry, and then you of course, yeah, this part is replaced by the discrete symmetry action and nothing else. Okay. Yes.
You're not assuming.
I'm not assuming it.
But according to the discussions in your lectures, in your local word Takahashi identity, you took alpha to be proportional to epsilon, and you expanded things you kept leading order in epsilon only, right?
So for the usual form of word Takahashi identity, it was necessary, and for that, the symmetry has to be continuous.
Yeah,
but here I'm still assuming some locality of this symmetry action because.
Yeah, but you expanded the action in alpha. So in the previous.
No, here I'm not expanding anything.
You did so when you are deriving local WT identity, right? You ignored all the alpha square.
So the infinitesimal, my usual form of word Takahashi identity, I expanded, yes.
So here you didn't expand it and defined U, right?
Yeah.
And how do you know that in the exponent, the exponent of U is linear in alpha?
Oh,
as you wrote down there.
Good question. So, well, okay. So that's related to the remark that I had to. I'm going to put. So But this is a formal form, and here actually I assumed, as Sok pointed out, I assumed that S of phi alpha is S of phi plus alpha partial mu j mu, and nothing else. Okay, plus 0, so nothing else. Okay, and this is not true, and this is not true even for the scalar theory. There is a Seagal term. Okay, so here, so there has to be correction, and in general, if you really try to write down this operator for a scalar field, then you will find the delta function squared. So actually, I'm talking about ill operator, and you have to regularize. Okay, so the remark here. Is that for the correct definition you need regularize. Like a function, use a function alpha. Okay, so for the U1 case, you can pick like put B region V, but you put a fuzzy boundary, and outside it's 0, and inside it's some alpha naught, and then here you interpolate between 0 and alpha naught smoothly, and then put and then take this fuzzy region to 0, something. And for the finite symmetry, you cannot you don't have a symmetry action between the not acting and acting some finite symmetry, but anyway you pick some interpolation, and then take this limit, and you have to make sure that this limit exists. And I'm not giving you the argument why it exists, but here I just assume.
So would it be linear in alpha? Alpha naught?
Probably not. Probably not. Sorry. Here. No, I'm not saying. Sorry. Oh, but yeah. At the end of the day, what it does is this. Okay? So yes. So in that sense, yes. But if you really, I haven't done. Yeah. That's an I think nice exercise, but I haven't done the such calculation. So if in scalar field theory, and you literally use this this expression, and whether you get the desired answer is unclear. I think it really depends on how you define this exponential and so on. So
if it carries more complicated dependence on alpha naught, I just take it as a definition of U.
Yeah.
Right?
Yes. But the point is the existence of such. And okay. So for the
sorry, couple of small questions.
Yes.
So when you write finite, do you mean finite group or generic groups? In the first word in that book.
Oh yeah, finite means finite transformation, but it immediately means that it can apply to finite group. Finite transformation. Yes.
I see. And the second minor question I had was the first line you write there that I must have missed the argument. How do I know that it only depends on the boundary?
Sorry. Yeah.
that your U alpha V depends only on the boundary?
Oh yeah, so here, yeah, in this conventional symmetry case, it's a bit yeah. So it's motivated from this equation that if you do the symmetry transformation inside and outside, and then
But that seems, I mean,
Yeah.
naively, I would expect that just to be a unitary matrix because it's a unitary transformation generically.
Well, so for the conventional symmetry case, it's kind of arbitrary when this space-time is connected, as it. Then, yeah, I'm just saying that instead of regarding this U depends on the entire region V, but I just regard this is depending on the boundary shape of the boundary.
I see.
Or position of the boundary.
Okay, thank you.
Yeah. In practice, I used the Stokes theorem. So yeah. So the formal application. Formally, you get from that definition you get like something like this, and I meant that I just use the Stokes theorem.
Sorry, there is a question from the Zoom, and
yes.
Well, I think very similar question, but for concurrentness, so I'll repeat the question. So can you repeat the argument why this operator U depends on boundary and also this orientation?
So the orientation, yeah. So here what I mean is that if you have some sigma 1 depends on I mean if you have sigma 1 in some contractive in some region, and then also you have to know the orientation, then which part you feel, okay, and then that's your B. So you can reconstruct B if the sigma 1 is bounded. Yeah, but
So I mean, your global symmetry is defined only on subspace, not entire space. So I think it is not guaranteed whether such a global symmetry is a theory. I mean, the symmetry of the theory.
No, I'm assuming it as here, and I start from theory with global symmetry, and this is the consequence of global symmetry, that the existence of topological operator corresponding to the finite symmetry.
But usually we are saying global symmetry is, this global symmetry is defined on entire space, not subspace. But you are considering
emphasis on, in my opinion, emphasis on the word global is not precise. Is not good, I think. Yes,
really?
It's so the action is invariant only when the symmetry you apply the constant symmetry action, okay, but it's also maybe I'm right here. So here the content of these kind of equation is okay. So the assumption is that it's a global symmetry. So the action is invariant for constant alpha. Okay, and but here, essentially, what it says that there's an okay. Oh, sorry. But what we essentially using deriving those kind of equation is that also this the symmetry action is locally defined. For example, your field is rotated point by point. Okay. And so there's a notion of like symmetry action on a point or on a region. Okay. Okay, and the correlation function is of course not invariant under such symmetry transformation, symmetry acting only on a point or only on some region, but it is controlled. That's the one content of this equation. Okay. So, okay, that's very good. So, okay, so for let me give you some concrete example and finish. So, I have 10 minutes. Okay, so for the reason about the regularization, it's a bit it's not practically easy, or it's not even practical to explicitly write down this U alpha for the continuous theory. Okay. Okay, so I emphasize that the existence of that is very important, but explicitly writing it down is not it's not practical, and depends on a lot of regularization you choose. So it's easier to talk about on lattice. Okay, so let me talk about the Ising model, 2D Ising model, and here actually I use the Euclidean space-time lattice. Okay, so it's rather a classical StatMech model, but I use the same reasoning and equations. Okay, so we have 2D lattice, just a square lattice. Okay, and well, I draw too much lattices. And okay, and this is Ising model, so you just have spins, and I put Boltzmann weight. Ij for the Ij adjacent. Okay, just is there a color chalk? This is white. Maybe not. Okay. So then So on the lattice, we can easily apply that definition. And what you get is, it's going to be very, let me see. Okay. I should have asked beforehand. Yeah, so I do not draw the lattice edge, the original lattice edge, and I put sigma 1 to be like this. Okay, so this is U sigma 1. Oh, I should have said that the Ising model has a Z2 symmetry, sorry. So there's a, so in my notation, sigma is plus minus 1 in writing the Boltzmann weight, and the Z2 symmetry that flips the sign, the spin. So this is, don't worry. Okay. So what is the correlation function when you insert this operator? Okay, this is 2D and this is codimension 1, so this line operator on the 2D lattice. Okay, so then what you do is essentially just apply this symmetry transformation inside this region. Okay. So well, this is Z2, so the actual orientation doesn't matter. But anyway, I draw the arrow. So okay, let me write this action G. Okay, so when you see the neighboring sites, when you see the line that dividing the neighboring sites, then this Boltzmann weight, for this Boltzmann, in this Boltzmann weight, you act the symmetry action on one of them. Okay, and so let's say this side of this is G. So J, and the symmetry action is this. So it's just you get plus J sigma I sigma J. Okay. So this correlation function is just almost just the usual Ising model with the this Boltzmann weight, but the Boltzmann weight is modified when these neighboring sites is divided by this line. Okay? So that's by a sign. Okay, then that finite Ward-Takahashi identity I was talking about says that you can deform this line one thing is that, like, whatever, and maybe more funny shape. Okay, you can also put like say the spin operator that just measures the spin here. So sigma and AX and maybe outside. Did that draw? Okay, sigma Y. Okay. Okay. And you can also shrink this operator inside, but then this line has to cross this the spin measuring operator, and then of course the symmetry acts on the spin measuring operator. So it's like but here you get G sigma x, which is just minus sigma x, sigma y. Okay, these are the equations. Okay. Okay, so let me summarize today's lecture. So the conventional, so far I've been talking only about the conventional symmetry is correspondent to topological operator. Okay. But we to make this direction correct, I have to put more words. Invertible. Okay. So the codimension one means, as we see that this thing is defined on the codimension one submanifold, and just like like that. And invertible is simply coming from the fact that we start from the group, or the symmetry. We've been assuming that symmetry action has its inverse operation. So you are on some sigma 1 is inverse of the same operator on the without reverse orientation. Yes, that's the invertible. Okay. Okay, so the generalized symmetry is defined by dropping these conditions. Okay, so to get a general symmetry, you either drop this condition, that condition, or both, and so that's the idea. Okay, so I stop here today.
Questions?
So if I define this Ising model on a chain or S1 or S2, then how does this go through?
Sorry. So what happens?
Say I have these spins on an S1.
Okay.
And then how does this go through? I mean, what happens to the boundary then? I mean, because the EU seems to exist. I mean, be defined on the boundary data.
Oh yeah. So okay. So that's a good question. So I implicitly. Okay, so in this, yeah. So actually, I only gave the definition of U only for the case that the sigma 1 is bounded by some region, but Yeah, but what in this example, it's obvious that actually such this operator is somehow locally defined. So with this action, so with this definition, you can also apply the case when this line say wraps some non-trivial cycle on your lattice system. Yeah. Yes. Yeah, and that's also I'm going to assume. So this topological operator is and that's what I meant by this defined on this surface, not within the entire region.
I see. Okay, thanks.
So for a non-orientable manifold, how do you define the invertibility conditions?
Oh yeah, here. Well, this definition, this is just a submanifold, and the submanifold has a. Oh yeah. Okay. So here, I define this invertibility that this should hold on the orientable submanifold. Okay, and you can have orientable submanifold inside non-orientable manifold, ambient manifold. So this works. I think that should be probably fine. I'm not exactly sure, because it should be defined locally. So yes. Yeah. In other words, this should be checked only for just tiny sigma 1 inside a patch. And I'm not, yeah, I think that's enough. Other question?
Okay, if there is no more question, let's thank speaker again.
Okay, so today lunch will be at cafeteria, as we did before. All right.
Lots of questions.
I know I kind of have
it's a good signal that many people are interested in this study. Yeah. Maybe some students want to ask questions.
So the content of partial identity in this case is that this is topological. So this line is topological. As long as it does not cross other operators. So I can so it's topological when it's not close to the other operator, and when it's close to the other local operator, then the difference is governed by the symmetry. That's the content of the work. So I just listen here and here. I just deform service area.
Okay, so then we put the two operator here and here, and also we can deform we can have any deformation with the operator. Okay, I see. There's no operator in this case.
Oh yeah. Here. There are sites of no operator, and I meant that I put the measure the spins when you do this the average expectation value. I put measure. So this is a 3-point function with coupled with the signal. Yeah, but here I of course assume that there is no term if you this function. Okay. That's one function. And I still assume. So here here applies formally applies. Then what do you get? What do you get? What do you get? Rewriting. Yeah, so yeah. But the fact that you get total derivative here
Okay, so welcome back. So good afternoon, everyone. So today, last speaker is Francisco Benini, and he will continue his lecture on the ADS black holes. Yes.
Okay, thank you. Is it working? Yes. Okay, so yesterday we introduced the superconformal index, gave you the definition of the index, and we found an exact formula for the index. And today, so first of all, I will make a few remarks on this index that I wanted to make last time, and then we will move to the next step. So this will be some remarks on the index. So first of all, I would like to tell you what is the general structure of this index. So for concreteness, let's take UN n equal to 4 super mills. And moreover, just to simplify our life, let's take all fugacities to be equal. So P equal to Q equal to, I define a new variable T, so T cubed. This will be the fugacities for angular momentum. And instead the fugacities for the R symmetries, we take them to be equal to T squared, and then make this choice, because you remember that really there are 4 fugacities, and we introduced a third one as an auxiliary variable, but then they should satisfy this condition here. So this choice satisfies the condition. So now we have a single variable. Essentially, this single variable counts the dimension of the operator. And the index, that I will call index of UN, takes the following form. So there is an initial part that takes the following form for sufficiently large n. So as you see here, I'm writing already the numbers, but this is the index of UN. And in fact, what it turns out that the initial part does not depend on n. So I will call this initial part index of U infinity. There is no dependence on n on it. And in fact, it's easy to understand why this is the case, because remember, in order to construct the index, we are constructing in the free theory BPS operators. And these BPS operators, we take the BPS letters, and then we form gauge invariants. And these gauge invariants are traces, multi-trace operators in these letters. And of course, when you construct traces of various products of these fields, there is no dependence on n. Okay? For instance, this object here comes from the trace of phi A, where phi is the scalar in the chiral multiplet, and there are 3 of them. So I get these operators here. So for instance, these ones come from trace of lambda plus and minus. This is the gaugino. And there are the two chiralities. So there are 2, and there is a minus sign. And then going on, there are more complicated traces. But of course, in this trace, there is no dependence on n. Now, it turns out that one can write a simple formula for this index. So this index of U infinity takes this simple expression. So it's an infinite product, and goes from 1 to infinity, 1 minus p to the, and now I'm writing the general expression, 1 minus p to the n minus q to the n divided by 1 minus 1 to the n, 1 minus y2 to the n, 1 minus y3 to the n. Sorry, this n is inside. Okay, so this expression here essentially is a product of Dedekind eta functions. So it's not that complicated. And it turns out that this object here, and I will come back to this in a moment, agrees with the index of gravitons, if you want free gravitons, in ADS 5. Okay, so you can consider wave functions of gravitons in ADS5, and you're looking for the BPS wave functions, and you evaluate the index with the very same quantum numbers in the bulk, and this is the result that you obtain. However, of course, this doesn't go on forever. The index has some dependence on n. And in fact, at some point, we get a dependence on n. And this starts happening at the power 2n plus 1. So the details of what this power is are not important, but the important is that this is of order n. And in fact, this contribution here, we can call it the one giant graviton contribution. So from the field theory point of view, how do I understand this? Well, the fact is that we are writing these traces, we are writing these operators, so you say these operators are traces of many fields. These are in general multi-trace operators. However, when the number of fields is of order n, since these are matrices, n by n matrices, because they are in the joint of un, then there are trace relations. And so all the multi-trace operators that we can write are not independent operators. Some of them will not be independent, will be among the operators that we have already listed. And so we should not just count the number of multi-trace operators that we can write, but we have to remove the operators that are fixed by the trace relations. And so this is the reason why here we start having some deviations from this counting here. This deviation depends on n, and it starts at an order that is of order n. So this is the origin of this contribution. And in fact, then at some point, at a power of order for n, we'll have an extra deviation, if you want, because now we will have relations among the trace relations. And I will call this a two giant graviton contribution, and so on and so forth. And the reason of this name is that in the bulk, we can interpret these contributions as coming from some object, some non-perturbative object. These are D3 branes wrapped in the geometry that go under the name of giant gravitons. So in our geometry, we have ADS5 times S5, and there are BPS configurations of branes, of D3 branes that we can construct. So these branes wrap an S3 into S5, and they are like a particle in ADS5. Moreover, these objects spin along this S3, and this spinning, together with the fact that the D3 brane coupled with the 5-on flux, prevents these branes from collapsing. So these are BPS stable objects. So these are some BPS D3 branes. And so they provide states in the bulk that are accounted by this counting here. Then, however, what we are interested in is the black holes. So we might expect that perhaps at some point there will be an extra, so after all this giant gravity contribution that goes like t to the n, perhaps at some point we have a new contribution where the power of t goes like n squared, and this should be the extra contribution of the black holes that we are after. However, it turns out that this is a bit too naive, and one way to see that it is difficult that at some point this extra contribution that has to be added is that while for these D3 branes, there is a minimal number of branes that we can put. We cannot put less than one brane. So there is a minimal point. So there is a point in this expansion where the first brane will appear, a point where the second brane, or having two branes, will appear. But for a black hole, at least classically, there is no minimal charge of the black hole. We can take a black hole and we can make it smaller and smaller, classically. Now, of course, at some point, when it is too small, the curvature is large, we don't believe the classical description anymore, but we cannot put a sharp constraint of a point where a black hole will start appearing. So it would be strange if there was some specific value here where we have to add something else, which is the black hole. And in fact, it turns out that if one writes down all these contributions, this expansion already contains the information about the black hole. And this we can put under the name of the giant graviton expansion. I might have some time at the end to mention, say a few things more about this, but I'm not sure. We will see. Yes, yes. So this contribution here, as I say, these are harmonics of a spin 2, well, it's the full graviton multiplet, so there are the spin 2, but also the other fits in the graviton multiplet. While these contributions here are the three branes that you insert in the geometry.
So in answer to how do you know whether it's giant graviton or black hole? The first one for answer to say people discovered black hole contribution at t equals to say 10 to 24. But how do you know it's not giant graviton or it's black hole? How do you know?
Yeah, so, okay, I'm not saying that you cannot define what a black hole state is. And as I said maybe in previous lectures, you might try to define at large n the concept of a black hole state by trying to take a near horizon limit and try to define the black hole states there in this way. And there are ways to define what a black hole state should be at small n. So you can try to define what a black hole state should be. I'm saying that in this way of expanding the index, in which you first of all have a contribution that you account as just gravitons in the bulk, and then you add contribution of the D3 branes, you don't need anything else to reproduce the full index. So you don't need this extra thing. Of course, this will be, all these objects contains powers of t that goes like n squared. You don't need to add something else. In a sense, the black holes will turn out to be condensations of gravitons and giant gravitons. Yes. Okay. So this is one observation. So now what we would like to do is take the index and essentially going at this level, so going at these powers here, and see whether the number of states that we have here, so we already commented on the fact that the index should at leading order gives us the net number of BPS states, so we would like to see whether we have enough to reproduce the degeneracy of black hole states. And of course, this is an old idea. It's not new. In fact, this was precisely the idea that led Kinney, Maldacena, Minwala, and Raju to, in fact, construct the superconformal index to count the states. And let me very briefly review the result that they obtained in their analysis. So remember, so we wrote the expression for the index, and let's keep working with UN. So we have to make an integral over the gauge group. So this reduces to an integral of the maximal torus. So this will be an integral. And let me write it in terms of some variables theta. Okay, this parameterizes the circles in the maximal torus. And then whatever else we have, we can put it into an effective action. We can call it an effective action of these eigenvalues. Okay? So these thetas are essentially the holonomies for the gauge field, and this effective action, there is both the integrand that we have and the van der Monde determinant, we just put in the exponent as a log. So all these theta I are between 0 and 2 pi. Okay? So this is a sort of matrix model with this effective action. And now the observation that they made was the following. If you take, so of course this effective action depends on the fugacities. These are the parameters of the index. And then they observed if you take real values for the fugacities, then this effective action turns out to have a real potential. And besides, this real potential is bounded from below, and it has a minimum. And so now the problem of taking the large n limit is very simple, because, okay, when you go to large n, you apply saddle point approximation, and this minimum will dominate. And so this is a saddle, and you can compute the contribution of this saddle. Now, it turns out that this is bounded from below at 0. So the minimal value of this effective potential is 0. So I call this theta. So theta minimum is 0. Moreover, what is the shape of this saddle? By this saddle, the eigenvalues are uniformly distributed along the circle. So theta e. So here we have a circle for where these cartans of where these holonomies live. At the minimum, they are uniformly distributed. Essentially, the repulsion in this effective action among the eigenvalues wins, and so they just distribute. Now, since the minimum is 0, there is no classical action. So if you want, you get 0 from here. Then you have to take into account the small quadratic fluctuations. And the result that you obtain is the following. So this will be the limit of the index of un evaluated at this real saddle. It turns out to be the index of u infinity. So this saddle reproduces the gas of gravitons. Okay. So this is very nice because it connects with gravity. So we see that in fact the index knows about something in gravity is the index of this gas of gravitons. However, it is not obvious if this will contain will also describe the black holes or not. And in fact, it turns out that it does not describe the black holes. So we don't see black holes here. So how do we know that? Well, this is not obvious because, okay, it is true that if you look at this expression, there is no dependence on n. So as we say, this expression here, this index does not depend on n. So okay, this is already a bit suspicious. However, when we look at black holes, remember the black holes have charges of order n squared. So if you want to compute the entropy for given charges that we extract from here, we have to, so this is the grand canonical partition function, we have to expand in this form, and we have to look at the coefficient in front of a power, and the power should be the charge of the black hole. So now the power is of order n squared, the charge will change, and so the coefficient here will depend in some way on n, just because n controls, if we fix the charge in unit of n squared, which power we have to look at will depend on n. Okay, so it's not obvious. However, we can evaluate what is the behavior of this index. So if we once again simplify to a single variable t, this index becomes the following function. That once again, you can write as a ratio. You can write as a ratio of, this is a 2, this is a 3, as a ratio of Dedekind eta function. Then you can use modular properties of this function to see what happens when t goes to 0. And then you can do the Legendre transform. You can extract the degeneracy, the coefficients. And what you discover is that the logarithm of the degeneracies, of the weighted degeneracies at charge n, this goes for n which is large as pi over 3 square root of 5n. Now n is the charge, so we have to take n that goes like capital N squared, but then you see that this implies that the entropy that is captured by this index goes like n, while the entropy of the black holes goes like n squared. So even though still the gas of gravitons gives you an exponentially large number of states, this is e to the n, not e to the n squared. Okay, so there are no black holes. So big N is the rank of the gauge group. So the gauge group, yes, so the gauge group is UN. And you remember that this N is essentially related to the ratio between ADS and the Planck length. So we have to take large n in such a way that the gravity is weakly coupled in the bulk, while this small n was the charge here. I mean, it's the No. So in fact, the point will be that this is not the full answer. So here I stressed this is the limit of the index computed on this saddle. But the point will be that there are other saddles. So this will not be the full answer. Yeah, I mean, people were puzzled for a long time because they get an answer that does not contain black holes. So what does it mean? Does it mean that there are no black holes? Maybe the black holes are not real BPS, or people was confused. But now we understand the point is that this is not the full answer. This is one contribution, but there are more. Yeah, so I have not defined black hole states. As I said at the beginning, it's not obvious how to do that. It can be done, one can make proposals, but it's not obvious. The point is that for a large black hole in ADS, the large majority, but the exponentially large majority of states are black hole states. So at leading order, up to non-perturbative corrections, all states are black hole states for large n. And so I will not care about distinguishing. But we see that this contribution cannot contain the black holes because there are not enough. States in here, at least in the index. Yeah. Then you might say, okay, maybe for the gas of gravitons, there are huge cancellations because the argument that I gave was for a black hole. So maybe actually if you look at the cohomology classes of gravitons, maybe there are enough, but this has been studied. There are no. Oh, yeah. Okay, so there are no gravitons here, but in fact, I mean, in retrospect, if you go back to the first lecture that I gave, well, we know that in terms of the new fugacities that we introduced, well, we described the thermodynamic of these black holes. We wrote down what is the grand canonical partition function. We obtained the entropy as a Legendre transform, but when we do that, the fugacities, the chemical potential, are not fixed. Well, the fugacities are not fixed to real values. They are fixed to complex values. And so this assumption of working with the real fugacities probably was a distraction, and we should work with complex fugacities. Now, of course, if you work with complex fugacities, then everything is complex here. The potential is complex. Does not make much sense to say whether it is bounded from below or not. It's just complex. So we are dealing with a complex integral. In general, we know that complex saddles contribute to a complex integral. And so it could well be that there is some other saddle that dominates in some region of parameter space. So this is what we want to look at. Do you have any questions so far? Okay. So now we would like to study in some other way this large n limit of the index. So let me rewrite once again the formula that we want to study. Of course, this is the main character of this story. So there was a prefactor. So these are the Pochhammer symbols. This is the order of the Weil group. Then there was an integral over the maximal torus. These are the integrals along these holonomies. So here I'm using a variable z, which is just, we're referring to what I had here. This is probably e to the I theta in respect to the holonomies. And I use a different notation, which is 2 pi I u. Following the way in which chemical potentials and fugacities are related in the rest of these lectures. So then the measures is written in the following way. And then you remember there are these elliptic gamma functions. There is one at the numerator for each chiral multiplet. Okay, this is a product over all the weights of the adjoint representation, because the chiral multiplets are in the adjoint representation. And then there was a denominator, and there is one gamma, elliptic gamma, at the denominator, and there is, well, actually one for each root of the gauge group. Okay, so this U is the chemical potential for the gauge symmetry. Okay, so we want to compute large N. And there are two approaches. Well, there are many approaches that have been studied, that have been taken. In these lectures, I will describe just two, because I cannot describe all of them. So one is the Cardy limit, and the other one is the Bethe-Ansatz formula that I will describe. I might have, maybe at the end I will have time to mention some other approach, but I'm not sure. So we will start with this, okay? So this Cardy limit, what is this Cardy limit? So the idea here, if you want, one way of thinking about it is that is an observation that the integrand, which is quite complicated, is these elliptic gamma functions, some special function. I gave you the definition, but they are complicated. But this drastically simplifies if we take a limit in which tau and sigma go to 0. Now, if you remember, we can roughly identify, and I will be more precise in the following, we can roughly identify the imaginary part of tau and sigma as invert temperatures. So this is a high temperature limit of the index. Yes, in fact, this is very similar to 2D, the high temperature limit in 2 dimensions. And this is why, so it's similar to the Cardy limit in 2 dimensions, and this is the reason of this name. So let me first describe it mathematically, and then I will describe more the physics of it. So mathematically, the observation is the following, as I said. So for instance, if we take the Kupo-Kammer symbol, and we take a limit in which tau goes to 0, well, it turns out that this simplifies. And you get something like the following. So you see that this simplifies a lot. Essentially, so this is up to exponentially small corrections. Essentially, this is the exponential of a rational function that has a term that goes like 1 over tau, and then a term which goes like tau. Now you can bring this here and say, okay, there is also a log tau term, but as you see, this is much simpler than what we had before. And there is a similar simplification for the elliptic gamma function if we take tau and sigma that goes to 0. So here is a little bit more complicated. We also need to take the electric fugacities to be real. And then the limit that we have is the following. So if we take x, so let me write the limit and then I comment. So here, so since x is real, to have the limit, we have to give it a small imaginary part. So this is why I use sigma and tau. Let me remind you that the imaginary part of tau and the imaginary part of sigma has to be positive for the index, for everything to be well defined. So these objects live in the upper half plane, much like in 2 dimensions. And this parameter small r will play the role of an R symmetry. So these parameters will be between 0 and 2. This detail is not particularly important. The important part is that once again, this becomes, up to exponentially small correction, the exponential of something which is essentially a polynomial in X, in the electric fugacities, with some divergences in the angular chemical potentials. So it will be some polynomial in X divided by tau sigma. And then there will be some other expression which is less divergent. This diverges either as 1 over tau or 1 over sigma times some other polynomial, plus other things that are of 0 order in tau and sigma. Okay, and as I say, so these are polynomials. This is a cubic polynomial. These are quadratic polynomials. Moreover, these are polynomials in a function that I will call x. So this is the fractional part of x. This is x minus the floor of x. So this essentially, you take x and you shift it by an integer until it is between -1 and 0. Okay, it's essentially the fractional part, but put between -1 and 0 instead of 0 and 1. So in particular, this is already periodic in X. This is the message. Now, okay, these limits can be improved, so one can do much better. But the important point is the following. So if we take this limit here that I described, so in particular, so as we said, tau and sigma go to 0. We take the imaginary parts of the electric fugacities to 0, so the electric fugacity becomes real. Tau and sigma should be kept fixed and real, and also the real parts of delta are fixed. But the imaginary part always positive. Then the expression of the index simplifies a lot, and let me just write it schematically. So this is an integral of something which is an exponential so something like this. So dramatically more simple than what we had before. So this is the exponential of, so this will be a piecewise polynomial function of the u. It's not just polynomial because there is this non-linear function, while in fact it's not continuous. And this potential diverges as tau and sigma goes to 0. So this becomes very large and it provides a very strong potential. Now, of course, the details of what this potential is depends now on the meta representation. One can do this computation for any n equal 1 theory. I'm not going to write the explicit expressions. But what happens is that for a suitable range of the parameters, for a suitable range of the real part of the delta A, what happens is that this V2 has a minimum at u equal to 0. And so once again, computing the saddle point, computing this in the saddle point approximation, it's very simple, okay? Because now we have a saddle where all this u goes to 0. And this approximation makes sense, once again, because the coefficient here is diverging in the limit. Now, however, notice that this minimum is very different from the previous one. So in the previous one, these u were distributed along the circle. Okay? So this was the previous minimum. But now they are all at 0. So this new minimum, they are all clamped up at the same point. So it's a very different saddle, and we might expect a different result. And in fact, the result that we obtain is the following. So the logarithm of the index in this limit is given by the following expression. So here there are these fractional part functions. So now it does go like n squared. And in fact, this expression should perhaps look familiar because it is essentially the exact grand canonical partition function that we obtain in gravity. The only difference is in gravity, we didn't have these fractional parts, but in fact, this fractional part locally is a linear function. So if you are expanding this locally around some value for this delta, because when we do the Legendre transform anyway, there is just a contribution from a local region, these are essentially the deltas up to some integer shifts. And so this is essentially minus the on-shell action of supergravity, which, as we said, is the grand canonical partition function of the system. And so in particular, if we do a Legendre transform, this exactly gives us the Bekenstein-Oki entropy.
A quick question.
Okay.
Yeah. Yeah, you have in one of your papers, you have some family of saddles if you want to compute the grand canonical or the version of this index from gravity. Can you understand the origin of these brackets as some particular saddles contributing depending on the value of delta?
Yes, we will get to that.
Okay.
So here, first of all,
thank you.
So in this Cardi limit, we are taking a limit in the parameters. And it turns out that in this limit, there is one saddle that dominates. So this is the saddle that we see here. Now, later on, we will relax this, and then we will be able to see, with the different approach, all the other saddles. Or more generally, I mean, one can study all other saddles. So this is just one, again. But this is the dominant one in this limit. So effectively, now this is the correct limit of the index in this particular limit, because this is the dominant saddle. In this region of parameter space. So the point is that so if we imagine to reduce to a single variable, and this is Q, which is 2 pi I tau. In fact, this is a point at which I will come in a moment. Different regions in this disk have completely different behavior. And so there is a line which is the line of real fugacities, was studied by Maldacena and collaborators. There are these other lines that I draw. These are the lines where you get the real black holes by doing the Legendre transform. And here, if you want the two meet at the small black hole, so when the black holes are very small, the large black hole is here and here. And now this limit that we are considering is a limit to this point. So it's a limit to the point of large black holes. But there are many different limits that we'll discuss in a moment, or there are points in the center, and one should understand all these points. This is quite complicated. There was another question, maybe? Okay.
Yeah, so this integrand, I mean, it's e to the power I something, right? So
sorry?
This integrand is e to the power I something, right? So the zero, I mean, it's highly oscillatory when you have tau and sigma going to 0. So is that a problem, or I mean, that's I, right? Exponential I pi by tau a.
Yes.
So generically, when you taking the tau or sigma going to 0, so that becomes highly oscillatory. Okay.
Yeah, so at the minimum is the point where it's not oscillating, right?
So it's
and
like
if you have an oscillating integral, the contribution comes from the point where this the first derivative goes to 0, and so it's not oscillating.
So from there, writing that is just basically some sort of a saddle point approximation.
This is the saddle point approximation.
Okay.
Yes. This is exactly the saddle point approximation around this minimum. Yes.
Okay. Thank you.
Okay. So this is very nice because we are able to obtain this Bekenstein-Oki entropy from the index. And in fact, this result was shown for the first time by Seok and collaborators. Now, as we discussed here, so we have discussed the thermodynamics from the point of view of gravity, and in particular these lines where the real black holes live. So now we can understand that these limits focuses on this region here. So this region is a region in which the black holes are very large. So this will be a region in which the charges of the black holes, J and Q, are much larger than n squared. N squared, I mean, I didn't say it, but is essentially the central charge of the four-dimensional theory. So this is, in fact, the same as the two-dimensional, very parallel or similar to the two-dimensional Cardi limit, which give you the density of states when the charges, or the dimension of the operators, are much larger than the central charge. Okay. Okay. So now, in fact, it turns out that this Cardi limit, so if you want, here we have done two things that maybe I was not super explicit in this. So first of all, we took a limit on the fugacities, but then we also did a large n limit, because after all, we want to take the large n limit, otherwise the result will be more complicated. But however, it turns out that this Cardi limit is quite interesting because it is independent of the large n limit. So we can do it in a generic n equal to 1 four-dimensional superconformal field theory at finite n. So I would like, even though this is not immediately related to our story, but it will be related in some way, so I would like to give you some information. So we can consider a generic four-dimensional n equal 1 superconformal field theory at finite n. And we can study this limit much in the same way as there is a 2D Cardi limit in, well, there's a Cardi limit in 2 dimensions. Now, perhaps this is a bit surprising. So this will be similar, as I said, to 2D Cardi limit. Because if you remember, the two-dimensional Cardi limit is obtained by using modular invariance. So essentially what you do is that you say, okay, I have some CFT that I study on the torus. When I go to low temperatures, the partition function is dominated by the vacuum character with a very mild assumption that there is, above the identity, there is a gap between the identity and the first operator. So you know for very low temperatures what is the behavior of the partition function. Then you use modular invariance, namely the partition function for tau is equal to the partition function of -1 over tau, where tau is the modular parameter of the torus. So this gives you what is the behavior of the partition function at high temperatures. And now you can just do, if you want, a Legendre transform and obtain what is the density of states. And it turns out that this analysis is valid if the dimension of the operators that you look at are much larger than the central charge. And so you can obtain in this way the general behavior of the density of states in a 2D CFT. Now, in fact, let me write down the partition function that you get. So the partition function that you get at high temperatures takes the following form. Plus non-perturbative corrections, where, okay, this beta, so I define Q as e to the 2 pi I tau, or e to the minus beta, so this beta is the inverse temperature. And so, in fact, even the expression that we obtain, if you compare, is somehow similar, so there is a divergence in this parameter beta, there is a divergence in tau over sigma, and here there is a central charge, and then there is a n squared. So already the form of the answer is similar. However, as I said, it's a bit surprising that in 4 dimensions there is such a limit, because there is no modular invariance in 4 dimensions. Okay, so it's a bit surprising, perhaps, that there is this limit. Yet, it turns out that there is, and moreover, the behavior of the density of states at large charges is, as in 2 dimensions, controlled just by the central charges, or more generally by the Toft anomalies of the theory. So it's some information which is very robust and is one loop exact, and in general we know about the theory. So how does this work? So very briefly, so one can define the index as the partition function, as we said many times, on S3 times S1. And we have these 2 parameters, sigma and tau. And one way to think about them is that they control the complex structure of the theory on S3 times S1. And when they are imaginary, we can write them in the following way. So essentially, we have a size that I will call L of the S3, and we have a size that we'll call beta of the S1. Moreover, this S3, in general, can be squashed. So I don't know how to draw it, but okay, there is a parameter B that determines the squashing of this sphere. And so sigma and tau can be written in terms of these geometric parameters in the following way. So essentially, if you see the product of sigma and tau corresponds to the ratio between these two manifolds, between the two radii, and instead the ratio between sigma and tau corresponds to this geometric squashing of the S3. So the Cardi limit that we discussed, in which sigma and tau go to 0, but with sigma over tau fixed, precisely corresponds to taking a limit in which, if you wish, the size of the S3 remains fixed, the squashing remains fixed, and just the S1 becomes small. And so in this sense, this is a high temperature limit, even though this is a supersymmetric temperature, because we are looking at BPS quantities. Yes, so this is a on this bag. I mean, we will. What I'm discussing here is the Cardi limit of the superconformal index. So there is a supersymmetric background, and this is sensitive to BPS state. So there is no temperature, but as I said, you can think of this as a sort of supersymmetric temperature. But yeah. In fact, I mean, from the analysis that I will briefly describe, one could wonder whether these can be extended to non-supersymmetric theories. Very limited work has been done, and it seems in some cases one can formulate a Cardi limit of four-dimensional theories without supersymmetry, but still with periodic boundary condition for fermions, but I don't think that there is much in the literature. Okay, so the standard definition of the index that we gave. So let me write it once again. So now so on one side, this is for a general four-dimensional n equal 1 theory. I also don't want to bother about global symmetries. I don't know what global symmetries the theory will have, so I only use charges in the superconformal algebra. And so the only thing that I will only introduce two fugacities, essentially for the angular momentum and the superconformal R charge. Okay. Otherwise, one can refine this with other fugacities for global symmetries, for flavor symmetries. Now, what happens is that when you look at this index, you can think of it from the Pite integral point of view in the following sense. Once again, we have the S3, we have the S1, and now the insertions. So the fact, so this is our supersymmetric Hamiltonian. So this generates shifts, translations along the S1. The trace tells us that this is compactified. And then all the other insertions, we think of them as boundary condition on the fields. So this is telling us that the statistics, we have periodic boundary condition for fermions. And now these objects here tell us that when you go along the circle, we should twist the fields according to their spin and their superconformal R charge by a phase which is e to the 2 pi I sigma and 2 pi I tau. So the fields should be twisted along the S1. However, in the Cardi limit, sigma goes to 0 and tau goes to 0. So this twist goes to 0, go to 0. And so in this limit, there are no twists on the fields, or the fields are periodic on the S1. Now, if you do the reduction, so we are taking a limit in which the size of this circle goes to 0, so you can write down an effective field theory on the S3. However, in this effective field theory, all the vector and matter fields will contribute with zero modes, as I said, because all the fields are periodic in this limit. So in general, you get a complicated effective field theory on S3 that you have to study. In general, this theory, if you put it on R3, it has flat directions. Now, when you put it on S3, the curvature gives some mass to the fields. So you do get an effective potential with a minimum that you can study. But the universal behavior is limited. And this was studied by Di Pietro and Komargowski back in 2014. And the answer that they get is the following: that the logarithm of the index takes the following form. So it's tau plus sigma over tau sigma. Once again, what you have to do, you have to study this minimum of the potential and do the saddle point approximation if you want around this minimum and take into account the effect of the massive modes. Okay, the result is the following. Here, A and C are the conformal central charges of the four-dimensional superconformal field theory. And this is, okay, an order 1 contribution in the sense of tau and sigma. So this will be a contribution, if you want, beta to the 0. So this is very similar to 2 dimensions. You see there is a term that goes like beta to the -1. So this is the diverging term, like in 2 dimensions. And then there is something of order beta to the 0. The other terms, okay, the series continues. However, 2 comments. So the first comment is that this term here is non-universal, in the sense that really depends a lot on what is the effective field theory on S3 that you get. It is related, for instance, to the S3 partition function or F partition function of this 3D theory, and has to be computed case by case. This piece here is universal. It's just controlled by these central charges. However, notice that for a holographic theory, A is equal to C at leading order. So for holographic CFT, A minus C doesn't go like n squared, but it goes like n to the 0. And so once again, we get a contribution to the index that doesn't go like n squared, and so it will not give rise to a density of states compatible with the black holes. Okay? So in fact, this particular limit is along this curve of real fugacities that I drew before. So this limit will correspond to taking a limit here. Okay? Whereas you see there is no sign of the black holes. So can we do anything about it? And the answer is yes. Yes.
So this first part is the contribution of one saddle, or I mean, I
didn't understand.
So the first part that you wrote as a beta to the 1 minus 1,
yes.
Is it the contribution from one saddle, or is it like
a contribution from
one saddle? Or do I expect multiple saddles that one needs to sum over, and which are maybe sub?
No. So this is a contribution from one saddle, which okay, I mean, you can assume that is the dominant one, and then on a case by case, you can check whether it is true or not. In fact, there are examples in which it is not the only one, and the situation is more complicated, and there are some conjecture of what conditions might guarantee that is the dominant one. But this is the contribution from a single saddle.
Okay.
But as I said, in certain conditions, I think that the conditions that are conjectural are that the theory is vector-like and A is smaller than C. I don't remember. But yeah, it is believed that this is the dominant one.
The dominant one. Okay.
But in this particular limit.
I see. Yeah.
Right? So, I mean, I'm not making any claim about other limits.
I see.
So this is in this particular point.
Okay. But there might be other saddles which are subdominating.
If you study other points, the physics is completely different. Yes.
Thank you.
In fact, we will come to this point in a moment. In fact, I mean, we have to come to that point now because we are not seeing the effect, the signature of black holes. But we already saw in the previous example that depending on in which region we go of the fugacities, we get different behavior. And in fact, so as I said, the point is that this is the superconformal R charge. And the superconformal charge is not integer, because as we said the other day, it's related to the dimension of operators. In general, it's rational. It can be fractional in special cases. So this means that this is not a single-valued function of the fugacities. So there is no periodicity in tau and sigma in general. Of course, if this is a rational, takes rational values, then there will be some periodicity, but in general, it can be larger than 1. And so what we can do is to first make some shift of this sigma and tau, and then take the limit to 0, which is the same thing as saying that instead of taking a limit in this particular point, we can try to take the limit at some other point. Okay, that might be more interesting than that point. Or maybe not more interesting, but different. Okay. So in fact, what we can do is the following. So we can shift sigma to sigma minus 1. And this gives what in the literature goes under the name of index on the second sheet. In the sense of complex analysis, that the object is multi-valued, and you go to another Riemann sheet. So, okay, if you do these shifts, you can see what is the effect, right? Because you shift sigma, so you can see that e to the minus 2 pi I j1 plus r over 2 is equal to, so this e to the minus 2 pi I j1 is the fermion number. And this one here gives you e to the minus I pi r. So if you make this shift, you get another one, minus 1 to the fermion number that cancels to the one that you already have. And instead, you get this one here. So you can call the new index, I mean, it's not really a new index, it's just a redefinition of the variables, but you can call this the index on the second sheet. It takes the following form. So instead of having minus 1 to the f, we have minus 1 to the, we have e to the minus I pi r, e to the minus beta, and the rest is the same. And now for this reason that here you don't have minus 1 to the f, but you have this is also called R index. Or maybe R symmetry index. I'm not sure, but okay. Yeah. No, that's the point. So
it's really different.
What is true is that bosons and fermions get an opposite sign. Because if you take in a multiplet, you take the bottom operator, and then every time that you argue with Q, you change the R charge by 1. So the various fields in the multiplet have opposite phases, but the phase that you get for a boson is not plus or minus 1. Is this depends on the R charge. So it's different. And as I said, it's just a shift, a change of the variables. I mean, it's not really a new index. It's just standing index at a different point, but it's different. Unless the R charges are all integer, but in interacting theory, this doesn't happen. Do you have to go to? No, so the analysis that was done by Komargowski and Di Pietro, of course, parallels the path integral derivation, but is more general, because what they do, they essentially derive what is the effective theory on this S3, and in particular, they argue that there is some effective potential, and so then the physics is controlled by, I mean, essentially it's the decided point approximation, but is the value of the fields that you get at the minimum of the potential, and then the contribution from all the oscillations of the masses of the fields, how they contribute.
What do you mean P?
on S3. So essentially, this is a reduction on the S1, and you write an effective theory on S3.
So you are looking at some action, right?
Yes, yes. But this is the effective field theory, so you don't need to know all about all the details. It's just you just look at the effective field theory. So essentially, you write down an effective potential for them. You know how the massive fields affect this effective potential, and yes.
Any other, I mean, the path by I'm to find out the saddle by looking at Hamiltonian only, not going into the test integral. There is some steps missing to me.
Well, I mean, you could use Hamiltonian methods, I guess, but it will be the same. Perhaps, okay, maybe something that I can say. So the point is that when you take this limit, so there is, so essentially you have some part of the potential. So some fields get a potential already on flat space, and the potential for these fields is diverging. Because when you take the limit, this goes like 1 over beta. So you have a very steepy potential, and so this piece of the effective field theory is very robust, because essentially the masses are very large, and so this contribution is essentially controlled by, in fact, this is controlled by the central charges, A and C. Essentially, you get some contact terms by integrating out the heavy fields. You get some Chern-Simons term. So this is very robust. This piece here comes from the fact that you have some fields that are still flat in R3 because of this reason that you don't have twists. So you have a lot of gapless fields. Then you go on this S3, so the curvature gives you some potential, but still this is a theory that you have to study. And in fact, as I said, this contribution here is non-universal, and you need to compute it with path integral techniques. In fact, this will be the S3 partition function of this effective field theory that maybe you, well, I mean, for sure you need localization to compute it. So this will be the, sometime called F, S3, or I mean, this is the partition function on S3. So this is precisely the hard part that maybe you're talking about. And for this, you need path integral and localization techniques. But this is more universal because this gets a potential that diverges in the limit. So it's a very strong potential. And in fact, this explains why this object is better than that one. Because now you see, even when you take the Cardi limit, so now you send sigma and tau to 0, but you still have this piece here. So this piece here tells you that all the fields get a phase which is -1 to the f e to the minus I pi r. And in general, since these R charges are generic number, in general this is not 0, so all the fields are twisted. And so all the fields get masses already when you go to flat space. You don't need the curvature of the S3. So the only field that is remained massless is the gauge field, because it doesn't have R symmetry. All the matter fields get masses. These masses are very large and diverge as 1 over beta squared. You're only left with the gauge field, but it turns out that the gauge field, if for instance we take SUN, it turns out that a Chern-Simons term is generated also for the gauge field, and in fact, Komargowski and Cassani argue that this is precisely level n, and so now also the gauge theory is gapped, because this Chern-Simons theory is a gapped theory. Moreover, it's a trivially gapped theory, is an SPT theory that has a single vacuum. So this is extremely simple topological field theory with a single vacuum. And so determining the effective field theory is very simple. The field is completely controlled by the contact term that you generate when you integrate out the massive fields, and you get an answer which is completely controlled by anomalies, or central charges. So in fact, the answer that you get, it's the following. So there is a term that there is a term that diverges 1 over tau sigma. So this goes like beta minus 2. Well, okay, maybe. I mean, here there are terms of different order, so maybe let me comment on that at the end. But okay, so this is controlled by the 't Hooft anomaly for the R symmetry, so trace of R cubed. Then there is another term of this form. This is controlled by the mixed R gravitational anomaly, which is controlled by trace of R. And then it turns out that the fact that also the gauge group is gapped, or the vector multiple is gapped, you get a contribution from essentially the one-phone symmetry of the gauge group. So this will be the order of the one-phone symmetry. And the claim is that this is the full perturbative answer up to exponentially small corrections. And as I said, this is possible because the theory is gapped, it's completely gapped. And if you expand this out, you will get terms that go like beta to the minus 2, beta to the minus 1, beta to the 0, like this term here, linear in beta, and that's it. So the perturbative expansion stops here. Okay, so then there are the non-perturbative terms. So this result is extremely powerful. Yes, okay. And yes, and in particular, so as I said, if we look again at this picture that I had before, this index corresponds to taking the limit at a different point, and it turns out that the point is the very same that we described before, is this point here. I mean, if we specialize, as I said, this is completely general, but if we specialize this to n equal 4 superior males, this corresponds to this large black hole point. However, notice that now here, well, this object here, so this starts at n squared. But in fact, if we take n equal to SUN n equal to pyramid, there is n squared minus 1. Now this turns out to be equal to 0 for the special case of n equal to 4 superior mils. So in particular, this contains terms of order n squared, but also terms of small order. So this will be order 0 in n. And in fact, for n equal 4 superior mils, this is a log n terms. So this expression here contains now much more data that it will be interesting to understand. No, so here this is a single saddle, and the claim is that this is the dominant one in this limit. In fact, I mean, in this limit, you see the way that I described, we are using effective field theory on S3. So yes, so I mean, in this particular case, which is more robust, this field theory proves that this is the dominant saddle at this point. That dominates, yes, usually yes. A special point, no, but so at this special point, this is the saddle that dominates. But you're right. You can ask, okay, are there other saddles? And in fact, so now we have described 2 points. So why we should just restrict to 2 points? What is special about these 2 points? Why not taking any other point? And it turns out that, in fact, one can work out this Cardi limit not at completely generic point, but at least at rational points. So one can study a limit in which, well, perhaps tau and sigma go to rational. And now, well, the limit that has been studied in detail is for the special case of, once again, n equal 4-dimensional n equal to 4 superyoung mills, and specializing to the case that tau is equal to sigma, so they simplify their lives. This was done by Arabi Ardeali and Murti. And one can study all these different rational points along the circle, and doing that, they get some expressions that are similar to this, but not quite the same. So, so different points give you a different answer. They all have this form, a divergence beta to the -2, etc., this structure, but the coefficients that you get here are different. And so this suggests, or perhaps it shows, that in fact there should be an infinite number of saddle, and different limits at different points on the disk, different saddles become dominant, and these are the saddles that you see in the various limits. So this suggests that perhaps if you go into in the middle, there is an infinite number of saddles that you should take into account. Now, of course, if you don't do large n, there is not much meaning in this statement, because I mean, in order to do set point approximation or large n or large whatever, you need a large parameter. So if you have a finite n field theory, you need to take the limit to have a saddle to begin with. But on the other hand, if you're doing large n, you already have a large parameter, which is n. And so now it makes sense to ask what happens in the middle. You don't need to take extra limit on the parameters. And you can ask, okay, what happens in the middle, what saddles do I have in the middle, and so on and so forth. And well, given the time, this will be the subject of the next lecture. Because I think my time is over, right? No, maybe I have 10 minutes?
10 minutes more.
Oh, I have 10 minutes. Okay, great. Can you?
What happens if we go to third sheet or fourth sheet? In that
If you go where?
Not second sheet, but third sheet or fourth sheet.
Yes, yes, so exactly. So, I mean, this nomenclature. So you see, you can consider a Cardi limit at any point you want. Now, from this language of sheets, okay, you can keep shifting if you want sigma. So for instance, if you go to a third sheet, you will essentially every time that you make this shift, you add another piece like this. So the next one, so the third sheet, you will have -1 to the f e to the -2 pi I r, which again, I mean, since this r is in general irrational, then the fields, all the matter fields will be twisted, and so you expect to have a nice limit. And for n equal 4 superior males, all possibilities has been studied, but not for a generic field theory. But it should be possible to do. Yeah. Perhaps one comment is that if you, instead of shifting sigma up, you should or down. I mean, you go in the other direction. You just get the complex conjugate of the index. So the -1 sheet is the complex conjugate, or I don't know, the 0 sheet is the complex conjugate of the second. Okay, something like that. All right. More questions? Okay, so perhaps I can then start with discussing the other approach that I want to discuss. Which is so as I described, in this Cardi limit, you study states whose charges are much larger than the central charge. So we would like also to study states whose charges are of the order of the central charge. And so in particular, we would like not to take any limit on the fugacities, but just take the large n limit. And once again, there are different approaches that have been developed in the literature, all very interesting, but I will describe one. So this is based on the Bethe-Ansatz formula. Okay, so so this approach is based on the following observation, that you can rewrite the formula for the index in a different way that turns out to be convenient to study large N. Now, it turns out that this formula is really useful if tau is equal to sigma. If tau is not equal to sigma, this formula becomes very complicated and so far has not led very, very far. So I will focus on this case here. And the formula looks like the following. So let me write it and then I will explain. Okay, so first of all, in this formula there is no integral, but there is a sum. And this sum is over the set of solutions to some equations. So this M beta ansatz equations is the set of solutions to certain transcendental equations that look like the beta ansatz equations of an elliptic integrable systems. So these are solutions of beta ansatz equations. These equations are as many as the rank of the gauge group. The variables or the unknowns of these equations are complexified holonomies. So I will call them UI, but they are complex. However, they live on a torus, on a two torus, whose modular parameter is given by the fugacity by the chemical potential for angular momentum. Okay, so there is this torus. So our variables live here. And for gauge group SUN or UN, one could write the general formula, but okay, the equation look like the following. So there is a quantity. Okay, I just give this name to this quantity, but okay, this is the equation. So you have to take the product of A from 1 to 3, the product over all these holonomies. And then, okay, perhaps let me write it first. So you have these functions here. These theta are essentially Jacobi theta functions. So these are functions quasi-periodic on the torus, but this ratio and product is single valued on the torus. So these equations are defined on the torus, and the equation is that this should be equal to 1, sorry. So you are supposed to solve these equations. This Uij is just Ui minus Uj. These delta A's are, once again, our electric chemical potentials. Well, you should solve these equations for Ui different from Uj. And as I said, if you look at this equation, they look like the beta ansatz equation for an elliptic integrable system. Elliptic because the momenta, this U will be the momenta, they live on a torus. So the space which is doubly periodic. Okay, so you're supposed to solve these equations, and then for each of the solution, you have to substitute into these two functions. The first function is the very same integrand as in the previous integral formula of the index. I'm not gonna write it again. This h is a Jacobian. So this h is the determinant over I and j of dqi over uij that you have then to evaluate at this solution. And this q is the equation. Okay, so there is this formula. So maybe we can look at this formula on the next lecture. So maybe I can just, if I take 1 or 2 minutes, just comment where this formula comes from, and then I will finish. It's okay. So, okay, one way to obtain the formula is just to start with the integral formula and do some standard manipulation, Cauchy integrals, collecting residues, and so on and so forth. So if you do that, there is nothing mysterious. But in fact, there is a nice physical interpretation that I would like to mention, which is the following. So the index is, once again, the path integral over S3 times S1. And, well, when we set tau equal to sigma, as we did, we can view this S3 times S1 as a holomorphic vibration of a T2 of modular parameter tau over a base which is S2. So essentially one of the two cycles is this S1, and the other cycle is the op vibration of S3 as the op fiber of S3 is a op vibration over S2. And so, so in fact, you can do this more generally for any manifold that admits this structure. In general now, so you could more generally consider some manifold, which is holomorphic vibration of T2 over a Riemann surface. And then, if you have this structure here, what you can do, you can reduce the 4-dimensional theory on the T2 and get an effective theory on S2. And it turns out that the theory that you get are on sigma G. And the theory that you get on sigma G is a topological A model. In other words, it is a 2D 2,2 theory with a twist. And these theories are described essentially by two functions. So this will be a topological A model of twisted chiral multiplets. And these twisted chiral multiplets essentially describe the abelian vector multiplets along the Cartan of the gauge group. And these models are described by two functions. So one is an effective twisted superpotential. So let me call the U the scalars in this twisted chiral multiplet. So one is an effective superpotential, and the other one is called holomorphic dilaton. And this holomorphic dilaton describes the coupling to curvature of this topological A model. And so the partition function that you started with, Z of M4, which in our case will be S3 times S1, so this will be the index, becomes, in this reduction, becomes a correlator in this topological A model. So first of all, it will be a correlator on S2. However, really here we have a Riemann surface, and it turns out that in a topological theory in 2 dimensions, you can change the topologies just by adding handles. And so there is an object which is called the handle gluing operator, and you have to add well, it turns out that the insertion that you have here is G minus 1. Essentially because when the genus is 1, the theory is flat and there is no coupling to the holomorphic dilaton. If you want this insertion corresponds to the coupling to the curvature and described by the holomorphic dilaton. And then there is another insertion that describes in which way this T2 is fibered over C2. In other words, the first chain class of this vibration appears, if you concentrate the curvature at a point, appears as a local operator in this topological A model. And it turns out that these operators takes the form of that Z. So in other words, this Jacobian turns out to be the handle gluing operator, and the integral in this special case is the operator that describes the first chain class of the vibration. So this is a correlator that you have to compute. And how do you compute this correlator in this topological theory? Where you just have to sum over vacua what you have here. So you have to sum over vacua, Z to the Chi to the C, H to the G minus 1. Now, how do you determine the vacua? Well, you have to find the critical point of the twisted effective superpotential. And okay, in 2 dimensions, it turns out that the equation that you really have to solve is that the exponential is equal to 1, which is slightly more general than saying that you are at a critical point of W. And it turns out that this equation here, if you work out what is the effective twisted superpotential, is the Bethe-Ansatz equation. So you can view this as essentially you're first solving the F-term equations, you find the vacua, and then you evaluate in each vacuum the contribution from these correlators, and you compute these correlators in the topological A model. Okay, I will stop here.
So any questions? May I ask questions? So yours, the Bethe-Ansatz formalism is based on the n equal 1 suji? So
Based on what?
Only use the n equal 1 supersymmetry?
Yes.
So can you say that for any n equal 1 theory, there is associated the integral model? Can you say like that?
Yeah, so this is a point that I never understood very well, so I'm not saying that there is no answer, but at least I was not able to find it. So, as I said, these look like Bethe-Ansatz equation for an integrable system. I personally do not know what is the explicit integrable system that gives rise to these equations.
But we know that there should exist.
There should be?
There should exist the integral system for with the same Bethe equation.
Perhaps, in the sense that, so you can view these in the spirit of the Nekrasov-Shetashvili, what is Bethe BPS correspondence. So the fact that if you have a theory with the 4 supercharges in generic dimension, this should correspond to an integrable system. However, this corresponds in all most of the examples that are in the literature are essentially for vector-like theories. So still 4 supercharges, but that are morally come from 8 supercharges, and then you give mass to the adjoint, something like that. Now, this equation here look like equation for a complex, complexified integrable system. So yes, you might say that there should exist one, but I was never able to find the one that corresponds to it, or having somebody telling me what is the integrable system. So yeah, so I don't know. So for sure, for any n equal 1 theory, we can write down these equations. And okay, if you can tell me what the integrable system is, I'm happy, but I don't know.
Any other questions?
I have a question. So here. So in Bethe-Ansatz formalism, you don't need to solve the saddle point approximation, right?
Yeah,
I mean,
so this is so this formula is not an approximation.
So
this formula is exact.
Yeah. But we may expect that the black hole entropy may be captured by saddle points in partition function, right? No?
Yes, so these are different. I mean, in principle, these are different approaches. So one approach is you go to large n and you apply saddle point approximation, which is an approximation.
So
the approach that I'm trying to follow, that we'll try to follow here, is that we rewrite the formula in this way, which is supposed to be exact up to some subtlety.
Yes.
And then you have this sum. And as we will see,
it gives
these, the elements here turns out to behave like saddle points. But in this description, they are not saddle points. Maybe there is some way to show that the solutions here are in one-to-one corresponding with saddle points. I don't know, but
yeah. Thank you.
But in this is not the saddle point approximation.
Yes. Thank you.
You didn't mention that in the general discussion, but you know this general partition function has very weird SL3Z stuffs, which you never mentioned, but whose meaning is never clear to anybody. But if you look at your Bethe-Ansatz formalism, it seems that there's SL2Z, which seems to be much more clear. Let's say from this torus structure or so on. So can you comment on what this SL2Z might possibly mean in this ADS5 CFT4?
Yeah.
stuff?
So well, I cannot give you an answer. But what I can tell you is the following. So first of all, the SL3Z is It's a bit different from the standard SL2Z because so in the standard story is that the partition function of the theory at tau is equal to the partition function of -1 over tau, and then okay, you extend to SL2Z. So it tells you that the partition function is invariant under it. Now, if you look at the elliptic gamma function, which is the index of a single chiral multiplet, you have a rather different equation. You have an equation that gamma, I don't remember what is the exact form of the equation, but something like 1 over tau, 1 over sigma. I'm very schematic, I'm not precise here. The point I want to make is that this is the product of two gammas. So it's not telling you that the index is invariant. Here, it's somehow the product of twice the index. Now, this was used by Gadde to show that you can construct an SL3Z invariance of an object, but this is a matrix object. So you have to make a matrix, a big matrix of objects, in which one of the entries is the index, and then the other entries are essentially the partition function with insertions of loops that give all other states. And then you have an equation like this, in which it becomes a matrix equation. Like this matrix for 1 over tau, 1 over sigma is morally something like the matrix times the matrix. So it's not clear how to use this for the index, because it's just one entry, but in this game you need all the other entries. Now, what about SL2Z? The index, I don't think it has SL2Z symmetry. Yes, so the beta-ansatz equations are invariant under SL2Z because you see there is this T2. So on this T2 there is SL2Z. So the equations are invariant, the solutions organize into representation, everything is nice. However, when you substitute these solutions in this expression here, this is not invariant under SL2Z. H probably yes, but this is Z no. Yes, exactly. In fact, we see it from here. You see, because this SL2Z changed the axon here. So, okay, this H describes the fact that here you have a Riemann surface, has nothing to do with it. But this Z, so when I wrote here, it was Z to the C, H to the G minus 1. This Z corresponds to the Furchen class. But you see here, so you start, so of the two circles, one is fibered and the one is not. But when you do a SL2Z transformation, maybe you exchange them. So it's not invariant. So in fact, this Furchen class that tells us what is the fibration should not be, and in fact, it's not invariant as SL2Z. Now, can we still use this SL2Z in some way? I don't know. Well, yeah, I'm not able to use it in a better way, but maybe you or someone else will be. I don't know. Yes. Yes, yes. I mean, Samir Murthy always stresses this fact that, I mean, in the when you study black holes in flat space, modular invariance is extremely useful and important, and it gives you strong results. The Radamatic expansion, all these kind of things. It would be very nice if there was also in this story for black holes in ADS something like that. I guess nobody has found it so far, but perhaps it's just hiding somewhere and is waiting that somebody can find it. Yeah, it's a great question. Yeah, I don't know. Yeah, so it turns out that there are two types of solutions to this equation. So, okay, usually in beta-ansatz there are discrete solutions. And here two. And discrete solutions are completely understood. So we know exactly, I know exactly how to classify all of them. The number of them is sigma 1 of n, which is the divisor function of m. I can tell you all the discrete solutions. There are no secrets here. However, it turns out that there are also continuous families of solutions. And these ones we don't understand. I don't know. Yeah, I don't know. No, I mean, I agree with you. This is a very interesting question. I'd love to know the answer. Of course, it would be nice to know what is the set of continuous solutions, what are the dimensions of each of these continuous families. There is a conjecture that was made by Ardeali, Liu, and then we also commented on it. The conjecture is that you take n equal 1 star theory. So this theory is for the n equal to 4 super-Young meals, and you give mass to all the fields. Now you have a massive theory. You can study you have a non-conformal theory, and you can study the vacua of this theory. So this theory has some completely gapped vacua. These are in one-to-one correspondence with this. This is easy to check. And then there are some vacua which are not gapped because there are photons. And the conjecture is that say again? Yeah, it's partly unbroken with some U1 groups, because all the non-abelian groups confine. But if you're left with some unbroken U1, those remains like the coupled photons. And the conjecture, but it's just a conjecture, is that each continuous family corresponds to one of these vacua, and the dimension of the continuous family is the number of photons. But yeah, I don't know how much is strongly motivated. It's just a conjecture, so yeah, I cannot say much more. I mean, we checked in a few cases, it seems to work, but just for very small n. So yeah, I don't think that there is very strong evidence for this.
So, yeah.
Thank you.
Yeah, actually, I think that Ardeali checked maybe this up to n equal to 6.
I have a question. Maybe follow up on that. Are these continuous solutions like in some relation with the fact that the determinant of this Jacobian, the Jacobian vanishes or something?
I think so. I think so, yes.
In that case, will the whole approach, the better answered approach, will be somehow in problems there?
Yes. So this is something that I said. So this formula, as written, was derived assuming that the solutions are discrete. Now, when you have continuous family, okay, as you say, there is a problem with H. Here, what is this sum? Should it become an integral? What is the measure? So you cannot apply this formula. Then you have to go back in the derivation. And you can see that in the derivation, well, essentially there is a point where you have to compute some contour integral. And so we assume that the contour integral has isolated points, and this is the residue at an isolated point. If it's not isolated singularity, then you have to compute the residue for this singularity of larger dimension. And so, yeah, the formula has to be corrected.
Thanks.
Yeah.
I have a question. Sorry. Can I ask a question, or is there? Yeah. Okay. Yeah, about the comment you made on this Rademacher expansion black holes in flat space, where there is a sum that appears from modular invariance, and then it's identified with different geometries and.
Yes.
And you said that it would be nice to have something similar here, but wouldn't you say that isn't the answer the Bethe ansatz itself, expansion itself?
No,
I was surprised that you. I mean, you could have said that because then you can relate each of those contributions to geometry. So then, what's playing the role of the Rademacher expansion here is precisely the
yes.
expansion.
So this is the idea. Now I was saying, so if you want to make this precise, so in the case of black holes in flat space, this Rademacher expansion. So first of all, you can derive from first principle the fact that there should be this Rademacher expansion, just using modular properties. And then in physics, as you know, it took a long time to figure out all the pieces. Moreover, this Rademacher expansion is a convergent expansion. So I mean, there is a lot of mathematical backgrounds behind it. In particular, is a convergent expression. This sum here that you get, for instance, is not convergent. So you have to take it with a grain of salt. And it would be nice if one could understand some underlying mathematical structure that tells you, maybe on first principle or maybe more in general, how to write down a convergent Rademacher-like expansion for the index here. For sure, this formula needs still some work because it's not convergent. And besides, if there was some underlying modular structure, I think it would be interesting on its own, right?
Any other question? Yeah. If not, then let's thank Francisco again.
All right. So again, tonight 6 o'clock we have a banquet at Lieto Firenze, and also I guess a lot of Indian students probably is taking a COVID test this afternoon and tomorrow afternoon, and I hope. I wish you good luck and okay. Hopefully things comes out okay. All right. See you guys at night.
Now, what people check is that you get one on two solution with the same